Hello there, and welcome to the Cosmographer. 3/4 of the Earth-like planets in this universe are older than ours, and on average they are older by 1.8 billion years, which means the interesting question was never whether anyone came before us. It was what would be left of them if they had. Our own planet cannot reliably record 3 centuries of industrial activity in its own rock, so an absence of evidence here proves very little. Less than 1,000th of this solar system has been searched at a resolution that would notice a 10-meter object. A grain inside a meteorite that fell on an Australian farm in 1969 turned out to be 7 billion years old. And for us to be the only technological species that has ever existed anywhere, the odds would have to run below 1 in 10 to the 22nd. Over the next 3 hours, we work through 10 parts: what survives, where it would be sitting, and what every unexplained signal has really turned out to be. Get comfortable and settle in. If you are the kind of person who would rather fall asleep to a real question than an easy answer, a quiet like and subscribe genuinely helps this channel reach more people like you. Because by the end of these 10 parts, the most durable artifact in the whole video will turn out to be one whose name you already know. Let's begin. Part 1. The Arithmetic of Deep Time. This is a video about archaeology. Not about who is transmitting right now, not about whether anyone is trying to reach us, not about signals arriving from somewhere in the dark. Those are questions about the present tense, and they have been asked many times. Tonight the question is older and, I think, more interesting. If a technological civilization existed somewhere in this universe long before us, what would be left of it now? And would we recognize the remains if we were looking straight at them? That is a different search, and it needs a different frame of mind. It treats the universe as a dig site rather than a switchboard. It assumes from the outset that anyone we might find is far more likely to be an ancestor than a contemporary. And it starts from a sentence that will come back again and again across the next 3 hours, in one form or another, until it has been earned. The record is thin. Over the course of this video, we will work through 10 parts, and each of them adds a layer to that same idea. We will look at what a civilization can leave in the rock of its own planet, and how little of it survives. We will look at what lasts in vacuum, and what does not. We will look at the material that arrives here from other star systems without anyone sending it. We will look at what astronomers have actually done every time something in the data looked artificial. And we will look at what is being built right now, in Chile, and in West Virginia, and in Florida, to ask this question properly, for the first time. But we start with arithmetic, because the arithmetic is the reason any of this is worth 3 hours of your evening. The universe is 13.8 billion years old. The Earth is 4.54 billion years old. Everything that has ever happened on this planet occupies roughly the most recent third of cosmic history. Every organism, every extinction, every ice age, every civilization. The universe had already been running for more than 9 billion years before the sun ignited. That is not a figure of speech. It is the setup for a specific and testable claim about where we sit in a sequence, and the claim was put into numbers in 2001 by an astronomer named Charles Lineweaver, then at the University of New South Wales. Lineweaver was interested in a problem that sounds technical and turns out to be the whole story. Rocky planets need heavy elements. Iron, silicon, magnesium, oxygen, the things a world is actually made of. None of those existed in the early universe. They were manufactured inside stars and scattered when those stars died, and it took generations of stellar life and death to build up enough of them for a planet like this one to be possible at all. So the early universe could not make Earths. There was nothing to make them out of. But there is a limit at the other end too. Systems that are extremely rich in heavy elements tend to produce large planets, and large planets tend to migrate inward, and a giant planet moving inward through a young system removes the small rocky worlds in its path. Too little material and no Earths form. Too much material, and the Earths that form do not survive. Between those two failures there is a window. Lineweaver worked out where that window sits and how many planets fall inside it, and then he asked when those planets formed relative to us. His answer is one of the quiet, load-bearing numbers in modern astronomy. About 3/4 of the Earth-like planets in the universe are older than the Earth, and their average age is 1.8 billion years older than ours, give or take about 900 million. I want to be careful about one detail, because it gets garbled constantly. That result is a statement about the universe, not about the Milky Way. It is a cosmic average, not a local census. Lineweaver was asking what the population of terrestrial planets looks like across everything we can see. Now sit with 1.8 billion years, because the number is easy to say and very hard to feel. 1.8 billion years ago on this planet, the most sophisticated organisms alive were single cells that had only recently learned the trick of keeping other cells inside themselves. There were no animals. There were no plants. There was nothing that could be described as a body. The entire history of multicellular life, of nervous systems, of vertebrates, of language, of agriculture, of writing, of radio, fits comfortably inside that margin, with room left over to run the whole thing several times end to end. So if the average Earth-like planet in this universe had a head start of that size, the interesting question stops being whether anyone got there before us. It becomes what a civilization does with a billion-year lead, and whether anything it made would still be recognizable now. There is a second number, and it pulls in the opposite direction, and the honest position is to hold both. In 2015, Peter Beruzzi and Molly Peoples at the Space Telescope Science Institute in Baltimore modeled the history and future of planet formation across cosmic time. They were not asking about civilizations. They were asking how many planets the universe has made so far and how many it still has to make. Their headline result is that when our solar system formed, only about 8% of the potentially habitable planets that will ever exist had formed. The other 92% are still to come. The universe is not winding down its planet-making. By their model, it will produce more than 10 times as many planets as currently exist. There are something like 10 to the 20th Earth-like planets in the observable universe already, and roughly a billion in the Milky Way alone. Beruzzi and Peoples also state a second figure, and the two get confused constantly, so let me separate them. They found that the solar system formed after about 80% of the Earth-like planets that exist today had already formed. 8% and 80% are different quantities, measured against different denominators. One counts every planet that will ever exist. The other counts every planet existing right now. Both are correct, and together they say something quite precise. We are late relative to the planets that exist. We are early relative to the planets that will. Remember that phrasing, because it comes back at the end of this video, and it means something different by the time it does. We are not early. We are late. Not first, not last. Somewhere in the middle of a very long process, which is the least dramatic and by far the most likely place for anyone to find themselves. There is one more line in that work worth quoting, because of how carefully it is worded. Their model implies at least a 92% chance that we are not the only civilization the universe will ever have. Not the only one that exists. The only one it will ever have. That is a statement about all of time, and it is stated as a flaw rather than a claim. Now, the consequence, and it is the frame that carries the entire runtime of this video. If civilizations arise at all, and if they arise across a window billions of years wide, then at any single moment, the overwhelming majority of them are not contemporaries of each other. They are separated. Take two civilizations divided by even 10 million years, which at cosmic scale is a rounding error, roughly the interval between us and the earliest apes. They would never overlap in any way that permitted contact. Neither would ever hear the other. The only thing either could ever find of the other is what was left behind. That point was made in print half a century ago, in a paper so short you could read it during a coffee break, with a title that reads like a manifesto for this entire video. In 1975, in the journal Icarus, Joseph Freeman and Michael Lampton published 2 pages called Interstellar Archaeology and the Prevalence of Intelligence. Their calculation was simple, and their conclusion was blunt. The spatial density in the galaxy of extinct civilizations and of planets carrying intelligent creatures without technical civilizations may be quite large. 50 years later, that paper is still cited as the origin of the idea that the correct search is for lasting relics rather than live signals. 2 pages in 1975, quietly pointing out that the dead should outnumber the living by a very wide margin, and that we were looking for the wrong thing. There is another dimension to this, and it stretches the window further in the other direction. Red dwarfs make up roughly 70% of the stars in this galaxy. They are small, cool, and extraordinarily frugal with their fuel, and they will burn for trillions of years. The universe is not yet 14 billion years old, which means that around most of the stars in the sky, the habitable era has barely started. The statistically typical world with a chance at life is one that has not had its interesting period yet, and will not for a very long time. So the population of civilizations, if there is one, is not distributed evenly through time. It is spread thinly across an interval so long that most of it has not happened. Some arrived early, on the first rocky planets that had enough iron to exist. Most will arrive long after the last star in this galaxy has finished forming. And we are somewhere in the middle, listening for a few decades, on one planet, with equipment we invented the day before yesterday. There is a way to feel that lateness in your own body. Every atom in you heavier than helium was manufactured inside a star that died before the sun existed. The calcium in your bones, the iron in your blood, the oxygen you are breathing while you listen to this. All of it was assembled in stellar interiors, thrown out in the deaths of stars, drifted through the galaxy for an unknown length of time, and then collected into the cloud that became this solar system. The Sun is a 3rd-generation star at the earliest. It is made of the leftovers of at least 2 rounds of stars that came and went before it, and so are you. And the scale of our own technological history sits oddly against all of this. The interval between the earliest known stone tools and the first radio transmission is about 3.3 million years. That is the whole of it, from the first sharpened edge to the first voice sent through the air without a wire. Set that against Lineweaver's 1.8 billion year margin, and the entire development of human technology occupies less than 1 part in 500 of the head start an average older world would have had. The Milky Way itself is around 13.6 billion years old, very nearly as old as the universe. There was a great deal of time for a great many things to happen here, long before there was an Earth for them to happen on. Let me make that last part concrete, because it is where the arithmetic stops being abstract and starts being personal. Radio has existed on this planet for about 130 years. Our transmissions have therefore reached a bubble roughly 130 light-years in radius, and they are extremely faint by the time they get there. 130 light-years sounds enormous. Set against a galaxy 100,000 light-years across, it is a sphere containing a few thousand stars out of a few 100 billion. Here is another way to hold it. Imagine the whole of human technological history, from the first telegraph to tonight, printed on a single sheet of paper. On the same scale, the age of the universe would be a stack of paper about 90 kilometers high. Somewhere in that stack is our sheet. Anyone searching for us has a target that thin, and they would have to be looking during exactly the right instant, at exactly the right point in the sky, with exactly the right instrument. We should assume our own targets are just as thin, and we should assume that most of them are not up there transmitting at all. Most of them, if they exist, are already in the sediment. Before we go any further into what a civilization elsewhere might leave behind, I want to imagine one. Not to claim it existed, simply to establish what we would be talking about, and to give the rest of this video something specific to hunt for. So let this next stretch be exactly what it is, which is imagination laid carefully on top of physics we do know. Picture a shoreline 6 billion years ago. The star overhead is an orange dwarf, smaller than the sun and cooler, and the light it throws is not white but a soft amber that makes everything look like late afternoon even at noon. It has been burning for 4 billion years already, and it has 40 billion more ahead of it. The day here is long. The tide comes in slowly, driven by a moon that formed the way ours did, out of the debris of an impact that nobody recorded. The chemistry is ordinary. That is the point of this scene. The rocks under your feet are silicate, with iron in them and a little nickel, the way rocks are. The water is water. The air holds nitrogen and carbon dioxide and a thin trace of free oxygen that some very simple thing has been exhaling for a few 100 million years. There is nothing exotic here. Nothing that would require the universe to break any of its habits. It is a perfectly unremarkable world, of a kind that Lineweaver's arithmetic says was already common at this point in cosmic history. And it is already ancient. When you stand on this shore, the cloud of gas and dust that will eventually collapse to make our sun has not begun to fall inward. It is still drifting, cold and formless, somewhere across the galaxy. Everything that will ever be part of the Earth is currently scattered between stars. This world has 2 billion years of history behind it, and there is no Earth yet at all. There is no place for the Earth. There is only the material. Now let the scene run forward. Something crawls out of that water, or does not. Something builds, or does not. The point is that whatever happened on this shore had 6 billion years in which to happen, and then 6 billion years in which to be forgotten. 6 billion years is enough time for a mountain range to rise and be ground flat and be replaced by another one several times over. It is enough for a continent to be assembled, torn apart, subducted, and remade out of different material. It is enough for the star itself to change color. If anyone stood on that shore, no trace of them would be waiting for us in any form we currently know how to look for. Not a building, not a bone, not a signal. The most we could hope for is something small and hard and deliberately made that got far enough away from that world before its planet finished digesting itself. That is the thing this video is looking for. And that brings us to a question we can actually test on a planet whose record we can hold in our hands. Because before we ask what an older civilization somewhere else would leave behind, there is a cleaner version of the same question available to us, much closer to home. 2 scientists asked it formally in a paper published 8 years ago, and the answer they got about our own planet is not the one most people would expect. Part 2. The Silurian Problem. There is a version of this question that we can actually run as an experiment, and it has the great advantage of being about a planet we can walk on. Instead of asking what an alien civilization would leave behind, ask what we would leave behind. Then go and look in the rock and see whether the answer is there. In 2018, 2 scientists did exactly that and published the result in the International Journal of Astrobiology under a title that is also the question. the Silurian hypothesis. Would it be possible to detect an industrial civilization in the geological record? The two names on it are worth knowing because the combination is unusual. Gavin Schmidt is the director of the NASA Goddard Institute for Space Studies in New York, one of the principal climate modeling centers in the world. Adam Frank is an astrophysicist at the University of Rochester who works on technosignatures. One of them spends his career reading the Earth's recent history out of data. The other spends his working out what a civilization looks like from a distance. The paper sits deliberately on the seam between the two fields, and it is a better paper for it. The name is a joke, borrowed from a 1970s television serial involving a reptilian species that supposedly predated humanity. Both authors are careful, immediately and repeatedly, to say what the paper is not. Their own words. While we strongly doubt that any previous industrial civilization existed before our own, asking the question in a formal way that articulates explicitly what evidence for such a civilization might look like raises its own useful questions. They are not proposing that anyone was here before us. They are proposing that we do not currently know how we would tell. And there is a second line in that paper that is, I think, the single most useful sentence in this entire subject, and it is worth holding on to for the next 3 hours. The Silurian hypothesis cannot be regarded as likely merely because no other valid idea presents itself. In other words, the absence of a better explanation is not itself an argument. That discipline is what separates this field from its noisier neighbors, and it runs through everything we are going to look at tonight. So what did they actually do? They started by defining terms, because the question is meaningless without them. An industrial civilization, for the purposes of the paper, is one able to harness external energy sources at global scales. Not tools, not agriculture, not cities. Energy, at planetary scale, drawn from outside the body. That is the thing that leaves a mark. Then they set a window. They asked what traces such a civilization would leave in strata laid down between the Devonian around 400 million years ago and the mid-Pliocene about 4 million years ago. That is a span covering most of the history of complex life on land, and it is the interval in which such a thing could in principle have happened without us necessarily knowing. And then, rather than speculating, they went and looked at the events geology has already recorded, to see what a planetary-scale energy event actually looks like when it is written into rock. The comparison case is an event called the Paleocene-Eocene thermal maximum, 56 million years ago. It is the closest natural analog we have to what industrial humanity is currently doing to the atmosphere, and the numbers deserve to be given in full, because the resolution problem only becomes visible when you see them. The whole sequence of events lasted between 100,000 and 200,000 years. The rapid carbon input at the beginning of it took perhaps less than 5,000. Global temperatures rose by 5 to 7 degrees Celsius. Carbon isotopes show a sharp negative spike, greater than 3 parts per thousand. The preservation of carbonate on the ocean floor collapsed. Between 30 and 50% of bottom-dwelling foraminiferal species, the small-shelled organisms that live in seafloor sediment, went extinct. And there are spikes in the abundance of vanadium, zinc, molybdenum, and chromium. Now hold that list next to what you would expect from an industrial episode. A sudden injection of carbon, a temperature rise, an isotope excursion, a metals anomaly, an extinction pulse in the oceans. It is the same list. That is Schmidt and Frank's uncomfortable finding, and they state it plainly. Almost every change they would expect from a hypothetical industrial civilization is, in their words, of the same sign and comparable magnitude to what the Paleocene-Eocene thermal maximum already shows. Read in rock, 56 million years after the fact, The fingerprint of a civilization and the fingerprint of a natural warming event look remarkably similar. The Paleocene-Eocene event is not the only comparison they draw, and the others matter because they establish that the pattern repeats. The end Permian extinction, 252 million years ago, the largest die-off in the history of complex life, unfolded over roughly 60,000 years, with a carbon isotope decrease of 5 to 7 parts per thousand. There is a second, smaller thermal maximum in the Eocene, and several more after it. There are ocean anoxic events in the Cretaceous and the Jurassic, intervals when the seas went short of oxygen and the sea floor recorded it in black shale. There is the late Devonian extinction, spread across the interval between 380 and 360 million years ago. Every one of those events is a planetary scale disturbance to the carbon cycle, written into rock, and every one of them has a natural explanation. Volcanism, orbital variation, the spread of land plants changing the chemistry of soil. The Earth has been running experiments in rapid global change for hundreds of millions of years without any help from anybody, and the results all look broadly alike. But the deeper problem is not similarity. It is duration. Human industrial civilization has lasted, so far, roughly 300 years. Depending on where you start counting, perhaps 250. And Schmidt and Frank state directly that the ability to detect an event onset of a few centuries or less in the geological record is questionable, and that isolating an industrial cause based only on apparent timing is therefore not conclusive. 3 separate mechanisms conspire to erase short events, and it is worth understanding each of them because together they are the reason this whole part exists. The first is bioturbation. Sediment on a seafloor or a lake bed is not a stack of undisturbed layers. It is constantly being stirred by burrowing animals, worms and mollusks and crustaceans working through the top few centimeters for thousands of years after it is laid down. Anything sharp gets smeared. An event that happened over 3 centuries is churned into an event that appears to have happened over 10,000 years, and its edges are gone. The second is hiatuses. Sediment is not deposited continuously anywhere. There are long intervals when nothing accumulates, or when what accumulated is later stripped away. The record has gaps in it, and the gaps are not marked. Your 3 centuries may simply fall into 1. The third is dating precision. At those depths and those ages, the error bars on the age of a layer are frequently larger than the entire duration of the event you are trying to find. Put the 3 together, and you get a conclusion that should give anyone pause. A 300-year industrial episode does not show up faintly in the geological record. It does not show up at all. It is below the resolution of the instrument. And the instrument has other problems, because most of the rock is simply not there anymore. The oldest large-scale land surface still exposed on Earth is in the Negev Desert, and it is about 1.8 million years old. Everything older than that, at the surface, has been eroded away, buried or destroyed. The ocean floor is worse. Because the seafloor is continuously recycled at subduction zones, dragged down into the mantle and remade, sediment evidence only exists for periods after the Jurassic, roughly 170 million years ago. Everything the oceans recorded before that has been melted. Then there is the matter of how much of the surface a civilization actually covers. Current urbanization accounts for less than 1% of the Earth's surface. And the exposed rock sections and drill cores available to us for pre-Quaternary surfaces are, as the paper puts it, orders of magnitude smaller as a fraction of the original surface than that 1%. We are not sampling the planet. We are sampling a handful of accessible outcrops and a scattering of boreholes. Their conclusion for anything older than about 4 million years is stated without hedging. The chances of finding direct evidence of such a civilization via objects or fossilized examples of its population is small. And fossils do not rescue the situation, which is the part most people find hardest to accept. Their example is the one to keep. For all the dinosaurs that ever lived, across 160 million years and thousands of species, there are only a few thousand near-complete specimens in all the world's collections. Work that out per unit time, and it comes to a handful of individual animals across thousands of species per 100,000 years. That is the resolution of the fossil record for the most studied group of large animals in the history of the science. Cities, meanwhile, would be a layer a few centimeters thick, made mostly of processed stone that looks like stone. And most of them sit on coastlines, which is exactly where erosion is most aggressive and where the record is most likely to be destroyed rather than preserved. The parts of our civilization most likely to survive geologically are not the monuments. They are the landfills and the deep mines. There is a single object that makes this point better than any statistic, and Schmidt and Frank cite it directly. The Antikythera mechanism was built somewhere around 205 years before the Common Era. It is a geared bronze calculator, capable of predicting the positions of the sun and moon, the phases of the moon, and eclipses, with more than 30 interlocking gears cut by hand. It was recovered from a shipwreck off a Greek island in 1901, and it took most of a century to understand what it was. Nothing of comparable mechanical complexity appears anywhere in the archaeological record again for well over 1,000 years. Not because nobody built anything similar, necessarily, but because one ship happened to sink in the right place, and one object happened to survive in the mud. A single artifact, preserved by chance, carrying an entire lost capability that we would otherwise have had no idea existed. That is the resolution of the record for our own species, 2,000 years back, on a planet we have been excavating intensively for 2 centuries. There is also a marker that would be genuinely diagnostic and yet will not last. Industrial fertilizer production alters nitrogen isotope ratios, and that signature is detectable in recent sediment. But nitrogen cycles rapidly through the biosphere, and the signal degrades on timescales of thousands of years rather than millions. It is a fine marker for finding a civilization that ended last week. It is useless for finding one that ended in the Cretaceous. So what would actually be unique? What would be unmistakable and unforgeable and readable 100 million years from now? Schmidt and Frank identify a short list, and it is shorter than you would like. Persistent synthetic molecules of the kind no natural process produces. Plastics accumulating in ocean sediment, which is now happening at a measurable rate. And, most durable of all, certain artificial radioactive isotopes. 2 in particular. Plutonium-244, with a half-life of 80.8 million years. And Curium-247, at 15 million years. Plutonium-244 is the interesting one, because there are no known natural sources of it outside supernovae. If it is in the rock in quantity, something made it, and the only things that make it are dying stars and reactors. A sufficiently large nuclear exchange would therefore write a line into the geological record that could still be read tens of millions of years later, and nothing else in nature would have written it. That is a strange fact to sit with. The most durable trace our species could leave, the one thing about us guaranteed to still be legible in the rock long after every city is gone, is the isotopic signature of the worst thing we could possibly do. And there is one place on this planet where exactly that signature turns up in ancient rock, and the story of what it turned out to be is the perfect cautionary note for everything that follows. At Oklo, in Gabon, in a uranium deposit roughly 2 billion years old, the ratio of uranium-235 is measurably wrong. It is depleted. There is less of it than there should be, and the fission products that would accompany its consumption are present in the right proportions. In 1972, French analysts noticed the discrepancy in ore that had come from the site, and it was significant enough to require an explanation. The explanation, when it arrived, was that 2 billion years ago, the natural concentration of uranium-235 in the Earth's crust was high enough for groundwater seeping through a rich deposit to act as a moderator, and for the deposit to sustain a slow nuclear fission reaction. It ran intermittently, in pulses, for hundreds of thousands of years, throttled by its own steam. Oklo is the only known site of natural nuclear reactors on this planet. So the one place where the isotopic fingerprint of nuclear fission appears in ancient terrestrial rock turned out to be geology rather than engineering. It is exactly the kind of discovery this video is about, and exactly the kind of caution the subject demands. Something looked artificial. It was investigated properly. It was ordinary, in a way nobody had anticipated, and the world learned something genuinely new from the fact that it was ordinary. I want to close this part with one more piece, because it takes everything abstract about the last 20 minutes and makes it uncomfortably concrete. There has been a long effort to formally define a new geological epoch, marking human influence on the planet. The Anthropocene Working Group proposed setting its boundary at around 1950, at the start of what is called the Great Acceleration, and placing the formal reference point in the top 15 centimeters of lake sediment at Crawford Lake in southern Ontario. Crawford Lake was chosen for a good reason. It is meromictic, which means its deep water never mixes with its surface water. Nothing stirs the bottom. The sediment stacks in undisturbed annual layers, like tree rings, and the marker preserved in those layers is plutonium from 20th century thermonuclear weapons testing. The Subcommission on Quaternary Stratigraphy voted on the proposal between the 4th of February and the 4th of March, 2024. The result was 4 in favor, 12 against, and 3 abstentions. The governing body confirmed the outcome on the 20th of March. The Anthropocene, as of this evening, is not a formal unit of geological time. The concept remains widely used, and one suggestion in the official statement was that it might be better described as an event, in the way the Great Oxygenation Event is an event, requiring no ratification at all. But formally, stratigraphically, our species has not yet managed to convince its own geologists that it constitutes a layer, which is a peculiar position from which to be confident that nobody else ever did. If the planet under our feet turns out to be a poor archive, then it is worth noticing that we are surrounded by much better ones, and that the nearest of them is close enough to see from your window. Part 3. The Archaeology of our own solar system. If the Earth is a poor archive, the rest of this solar system is an extraordinary one. And the argument for searching it, which is a good deal stronger than most people assume, has been made in the professional literature for over 50 years by people whose names are worth knowing. Start with the physics of preservation, because it constrains everything else. The Moon has no atmosphere. It has no liquid water, no plate tectonics, no weather, no wind, no rain, no chemistry that eats things. Everything that destroys objects on the surface of this planet is absent there. What the Moon has instead is a slow, continuous rain of micrometeoroids, grains of dust arriving at tens of kilometers per second, and over long enough spans that rain does grind things down and stir the surface up. The process has a name. Astronomers call it gardening, which is a gentler word than the process deserves. The canonical description was laid out by Donald Gault and colleagues in 1974 and substantially updated in 2018 by Emily Costello, Rebecca Gent, and Paul Lucy. Between them, they give us the numbers that make this part possible. The top centimeter of lunar regolith is mixed on a timescale of about 1 million years. The top meter is turned over on a timescale of about 1 billion. Exposed rock surfaces erode at roughly 0.3 to 0.6 millimeters per million years. Say that middle number again, because it is the one that matters, and it will come back at the end of tonight. 1 meter per billion years. Sit with what that actually means. An object placed on the lunar surface would need something on the order of 1 billion years before the surface itself had churned deep enough to bury and destroy it. Anything set down there within the last few 100 million years, anything from the age of the dinosaurs onward, should still be sitting essentially where it was put. Degraded, dusted over, scoured by micrometeorites, but present. Findable. Costello and her colleagues added a refinement that makes it stranger. They found that the mixing in the top meter is dominated not by the primary impacts themselves, but by secondaries, the debris thrown up by those impacts landing elsewhere. Which means gardening is not smooth. It is patchy. Some areas get worked over repeatedly, while others sit almost undisturbed for far longer than the average would suggest. The Moon is the best filing cabinet within 400,000 kilometers of where you are sitting. We have walked on it 6 times, and we have never once searched it. Let me put you on that surface for a moment, because the numbers only mean something if you can picture the place they describe. You are standing on the far side of the Moon. The first thing you notice is that the horizon is close. The Moon is small, so the ground curves away from you within a couple of kilometers, and there is a constant faint sense of standing on top of something rather than inside it. The second thing you notice is the quality of the shadows. There is no atmosphere to scatter light, so there is no soft edge anywhere. Where the sunlight falls, the ground is a hard, blinding gray. Where it does not, the shadow is not dark, it is absolute, a shape cut out of the world with nothing inside it. Your own shadow lies across the regolith, with edges like a blade. If you step into the shadow of a boulder, you disappear. The third thing is the stars, and the fact that they do not move. There is no twinkling here, because twinkling is an atmospheric effect, and there is no atmosphere. The stars are fixed points, unblinking, and they stay exactly where they are while you watch. The Earth is not in the sky at all, because on this side of the Moon it never is. And under your boots is the surface itself. Fine grey powder, sharp-edged because nothing has ever weathered it smooth, packed hard a few centimeters down. It has been stirred to a depth of about 1 meter over the last 1 billion years, and to a depth of about 1 centimeter over the last 1 million. Which means the footprint you have just made will outlast, comfortably, most mountain ranges on the planet you came from. Nothing will blow it away. Nothing will wash it out. It will simply sit there, gradually softening, for tens of millions of years. Now the imaginative step, and it is only a step, because everything up to this sentence is measured. If anything had been set down on this surface at any point since the dinosaurs walked on Earth, it would still be here. Not intact necessarily, not functioning, but present, within 1 meter of where it was placed, under a covering of dust thin enough to brush off with a glove. It would not be hidden. It would simply be somewhere on a surface of 38 million square kilometers, in the dark, on a body nobody has ever systematically examined for anything except geology. That is not an argument that anything is there. It is an observation about what the Moon would do with it if it were. We do not have to take the preservation numbers on trust, incidentally, because there is a controlled experiment already running on that surface, and it has been running for over half a century. Between 1969 and 1972, 6 crews landed on the Moon and left roughly 180 tons of material behind. Descent stages. 3 lunar roving vehicles parked where their drivers stopped. Experiment packages, cameras, tools, boots, bags. 6 flags. and several 100,000 footprints. All of it is still there. The Lunar Reconnaissance Orbiter has photographed the landing sites from orbit, and you can see the hardware, and you can see the tracks the astronauts made walking between the lander and the instruments, and you can see the wheel ruts of the rovers. 50+ years of continuous exposure to hard vacuum, to a surface temperature that swings by about 300 degrees between lunar day and lunar night, to unfiltered ultraviolet, to the micrometeoroid rain, and the layout of the site is essentially unchanged. The only visible degradation is to the flags, which were made of nylon and have been bleached white by ultraviolet. The metal, the ceramics, the glass and the plastics are fine. The footprints are exactly where they were made. That is what a 50-year-old artifact looks like on the Moon. Now scale the exposure by a factor of 1,000,000, and you are still comfortably inside the billion-year gardening timescale. The formal proposal to actually go and look came in 2013 from Paul Davies and Robert Wagner, both at Arizona State University, in the journal Acta Astronautica. The title is exactly what you would expect: Searching for Alien Artifacts on the Moon. Their argument is one of opportunity rather than probability. The Lunar Reconnaissance Orbiter has been in operation since 2009, and it has produced roughly 2 million images at sub-meter resolution, about half a meter per pixel, covering something like 90% of the lunar surface. That dataset already exists. It was gathered for geology and for landing site selection, and it is examined by geologists looking for geological things. Davies and Wagner proposed examining it for anomalies instead. Their method was practical. Use machine processing to prune the image set down to a manageable size, then put human volunteers on what remains, explicitly modeling the approach on the distributed computing and galaxy classification projects that had already demonstrated that thousands of amateurs will reliably do this kind of work for free. They were entirely honest about the odds. Their own assessment was that the chance of finding anything is very small. Their argument was not that success is likely. It was that the imagery has already been paid for, the cost of looking is close to zero, and the value of a positive result would be difficult to overstate. When the price of a search is nothing, even a very small probability is worth buying. It is also worth saying that the Moon is not the only body with this property, merely the closest. Mercury has no atmosphere and no water, and its surface preserves impact structures on comparable timescales. The airless moons of the outer planets are better still, because they are further from the Sun, further from the main sources of impacting debris, and colder. Almost none of them have been imaged at anything approaching the resolution the Lunar Reconnaissance Orbiter achieves at the Moon. For most of the small bodies in this solar system, the best pictures we have would not resolve a bus. And Hak-Misra and Kopparapu single out the Lagrange points specifically because they are the one category where the argument is strongest and the search is weakest. The fourth and fifth Lagrange points of a two-body system are gravitationally stable over the lifetime of the solar system. Material that drifts into them tends to stay. They accumulate dust and small bodies, they require no energy to remain in, and they have never been systematically surveyed at high resolution. If you wanted a location in this system where an object could sit undisturbed for 4 billion years, they are the obvious answer, and they are effectively unexamined. There is one further point in favor of the Davies and Wagner proposal that has only strengthened since they wrote it. The Lunar Reconnaissance Orbiter was launched in 2009 with a planned mission of 1 year. It is still operating. The searchable image archive they described has roughly doubled in size since their paper appeared, and it continues to grow. The dataset is not a fixed thing waiting to be examined once. It is an accumulating record of a surface that does not change, which is the ideal circumstance for noticing anything that does. The more systematic version of the argument had appeared a year earlier in the same journal from Jacob Hak-Misra and Ravi Kumar Kopparapu. on the likelihood of non-terrestrial artifacts in the solar system. What they built is a framework relating how confident we are entitled to be that nothing artificial exists in a given volume of space, to how much of that volume has actually been searched at a resolution capable of noticing an object 1 to 10 meters across. It is a simple idea, and the results are not comfortable. Earth's surface has been searched at a fraction approaching 1. We have been over this planet thoroughly, so our confidence that there is no such object sitting on it is reasonably high. The Moon has been searched at no more than 1/2, Mars at no more than 1/10, and then the numbers fall off a cliff. The asteroid belt, the Kuiper belt, and the gravitationally stable Lagrange points have all been searched at a fraction of less than 1,000th, which they describe as leaving almost no confidence at all. Their own image for this is the one to keep. Searching the entire solar system at that resolution, they write, is analogous to finding a needle in a 1,000-ton haystack. Enough hay, they add, to cover an American football field to a depth of 3 feet. We have looked at a few handfuls of that hay, and on the strength of those handfuls, we have concluded that the haystack is empty. Which raises an obvious follow-up question. If you were going to leave something in a star system, where would you put it? That question was addressed as early as 1960. On the 28th of May that year, in the journal Nature, a Stanford radio astronomer named Ronald Bracewell published a short paper called Communications from Superior Galactic Communities. His argument was economic. Broadcasting continuously across interstellar distance in the hope that someone is listening at the right frequency at the right moment is enormously expensive and enormously unlikely to work. Sending a small autonomous probe to a promising system where it can wait is cheap by comparison and requires no coordination at all. Park the messenger and let it sit until there is somebody to talk to. There is a detail in Bracewell's original paper that is easy to skip past and worth pausing on. He was writing in 1960, the same year that Frank Drake pointed a radio telescope at 2 nearby stars and began the modern search. Bracewell was not opposing that effort. He was pointing out that it embeds an assumption nobody had examined, which is that a civilization wanting to be found would choose the method that costs the most and works the least reliably. His alternative asks almost nothing of the sender. Build one object. Send it once. It arrives whenever it arrives, and then it waits, because waiting is free. The energy budget of a probe that sits still for 10 million years is essentially zero, while the energy budget of a beacon transmitting for 10 million years is astronomical in the literal sense. If you were designing a system to make contact across deep time rather than across distance, the physics points firmly in one direction, and it is not the direction we have spent 60 years searching in. The idea now carries his name. Astronomers call them Bracewell probes, though Bracewell himself never used the term. In 2019, James Benford took that idea and asked the practical follow-up in the Astronomical Journal, in a paper called Looking for Lurkers. If something were parked in this system, where specifically would it be sitting? His answer is the class of objects called co-orbitals. These are bodies that share Earth's orbital period around the Sun without actually orbiting the Earth. Some of them are quasi-satellites, which appear from here to loop around us over the course of a year while genuinely orbiting the Sun. Others follow horseshoe paths, drifting slowly ahead of us and then slowly behind. What they have in common is that they stay close, indefinitely. Benford's case for them is entirely practical. A co-orbital passes closer to this planet than anything except the Moon, every single year, for millions of years at a stretch. It offers raw material for repairs. It offers uninterrupted sunlight for power. It offers a stable gravitational anchor so that nothing needs to expend fuel holding position. And it offers concealment because a small dark rock among other small dark rocks attracts no attention at all. If you wanted to leave something in this system to watch what happened here over geological time, that is where an engineer would put it. His named target is the best one available, and its story is genuinely strange on its own terms. Kamoʻoalewa, formerly catalogued as 469219, was discovered by the Pan-STARRS survey at Haleakala Observatory in Hawaii on the 27th of April 2016. It is somewhere between 40 and 100 meters across. It is the smallest, the closest, and the most stable quasi-satellite of the Earth that we know of. Its Hawaiian name means, roughly, the oscillating celestial object, which describes exactly what it appears to do. It is also a fast rotator, which makes it difficult to observe, and it is faint, which makes it harder. It took 5 years to get a decent spectrum. When that spectrum arrived, in November 2021, from Ben Sharkey and Vishnu Reddy at the University of Arizona, it did not look like an asteroid. Asteroids have characteristic reflectance signatures depending on their composition, and Kamoʻoalewa did not match any of the usual classes. What it matched was lunar silicate. And the closest match of all was to the Apollo samples returned from the Fra Mauro highlands. The best current explanation is that Kamoʻoalewa is a piece of the Moon. Knocked off by an impact at some point in the past, thrown clear, and now keeping pace with the Earth in an orbit of its own. And we are going to go and touch it. China's Tianwen-2 launched on the 28th of May 2025. It spent roughly 400 days and about 1 billion kilometers in transit, and it is now station-keeping some 20 kilometers from the object, having already returned its first images. It is scheduled to depart with a sample in April 2027, and to deliver that sample back to Earth in late November of the same year. After that, it has an extended mission out to a main belt comet, with orbital insertion planned for January 2035. So the single most plausible parking spot for a dormant object in this entire solar system, identified by name in a paper 6 years ago, is currently being surveyed at close range by a spacecraft that was sent there for entirely geological reasons, and a piece of it will be in a laboratory within 18 months. I want to be precise about what that does and does not mean. None of this is evidence of anything. Nothing has been found. What these papers give us is not a discovery, but a measurement of our own ignorance, and the measurement is severe. Every confident statement about the emptiness of this solar system rests on a search that, by the numbers of the people who actually calculated it, has barely begun. Which raises the next question, and it is the one the following part is about. If you were going to look for something left here a very long time ago, what exactly would you be looking for? What would an object have to be made of to still be there at all? Part 4. What actually lasts? We now have a place to look. What we do not yet have is a search image. If something was left in this solar system, or any other, 100 million years ago, what would it be made of, and what shape would time have left it in? The remarkable thing about this question is that we do not have to speculate. We have already answered it, in practice, 5 separate times, mostly by accident, and within 7 years of the first time anyone left the atmosphere. But start with the physics, because it sets the boundaries on everything else. On the surface of this planet, almost nothing lasts. The atmosphere is the problem. Oxygen is a corrosive gas, and it attacks metals continuously. Water dissolves, penetrates, freezes and expands, and splits anything it gets into. Temperature cycles work joints loose. And on top of all of that, there is biology, which will eat, root through, colonize and dismantle essentially any structure left unattended. Under those conditions, a building lasts centuries. A worked metal object lasts, at the outside, a few thousand years, and only if it is buried somewhere dry and stable. The Antikythera mechanism survived 2,000 years because it sank into anoxic mud, and it came up as a corroded lump that took a century to read. In vacuum, every one of those processes stops. There is no oxygen, so there is no oxidation. There is no water, so there is no dissolution and no freeze-thaw. There are no organisms. What remains is a much shorter list, and everything on it is slow. The first is micrometeoroid abrasion, the same dust rain that gardens the moon, which sandblasts an exposed surface at a rate measured in fractions of a millimeter per million years. The second is cosmic ray bombardment, which does not remove material but gradually damages the crystal structure of a solid, darkening surfaces and, over long enough spans, degrading fine detail. The third is simply the accumulation of dust, which is only a problem if there is somewhere for dust to come from. And in deep space, between stars, far from any surface and far from any star, even those slow processes slow further. The dust density is negligible. The cosmic ray flux is real but modest. An object out there is not being preserved by anything. It is simply not being attacked. So the answer to what lasts is fairly specific. A hard, chemically inert solid. In vacuum. Away from stars. Ideally a metal that will not oxidize even if it eventually encounters an atmosphere again. Information carried as physical relief, cut into the surface, rather than as anything requiring a machine or a format or a power supply. That is the search image. And what is remarkable is that every serious attempt our own species has made to speak to the deep future has converged on exactly that description, independently, without anyone setting out to design a 100-million-year artifact. The first one was small, and it went first. In March 1972, Pioneer 10 launched carrying a plaque of gold anodized aluminium, 6 inches by 9, 5/100ths of an inch thick. Pioneer 11 carried an identical one the following year. Carl Sagan and Frank Drake designed the content. Linda Salzman Sagan drew the artwork. NASA gave Sagan 3 weeks to produce the whole thing, from the idea to the finished design, and the plaques were engraved by a company in San Carlos, California, that in the ordinary course of business made trophies and nameplates. The design shows a hydrogen atom in 2 spin states as a unit of measurement, a map of 14 pulsars locating the Sun, a diagram of the solar system with the spacecraft's path drawn on it, and 2 human figures. The man has his hand raised. Sagan chose that gesture deliberately because it does 2 jobs at once. It reads as a greeting, and it demonstrates the opposable thumb and the range of motion of the human arm. Those 2 plaques are, at this moment, the most distant engraved objects made by human beings. Neither spacecraft is in contact anymore. Pioneer 10's last signal came in 2003. They are both coasting outward, dead, with the plaques still bolted to their frames. It is worth saying why gold specifically, because the reason is chemistry rather than sentiment. Gold does not tarnish, and the explanation sits in the structure of the atom. Its outer electron shell is unusually stable, which means gold is extremely reluctant to give up or share electrons with anything, which is what corrosion actually is. The property that has made the metal valuable to human beings for 6,000 years, the fact that it stays bright while everything else goes green or brown or crumbles, is the same property that makes it the correct material for a message intended to be read 100 million years from now. Nobody chose it for that reason. It was chosen because it was available, workable, and would survive the launch. But when you sit down and ask what a 100-million-year artifact should be made of, the answer that falls out of the periodic table is the metal we happen to already be using. There is a small, human detail attached to the Pioneer plaques that I have always liked. Sagan was given the idea the assignment, and the deadline almost simultaneously, and the launch schedule did not move for him. 3 weeks, from a conversation to a finished engraving, for the first object of its kind our species had ever attempted. The result has been criticized in every decade since, for the choice of figures, for the assumptions baked into the diagrams, for the pulsar map's readability. Most of the criticisms are fair. None of that changes the fact that it exists, and that it was done at all, and that the alternative was launching 2 spacecraft out of the solar system carrying nothing. Somebody in a hurry decided it was worth 3 weeks. Both plaques are now further from the sun than any human being will travel in the lifetime of anyone listening to this, and they will still be legible long after everything anyone alive has ever built has gone. The golden record, 5 years later, is the serious version, and it deserves the most time. It is a 12-inch phonograph disc of gold-plated copper. One flew on Voyager 1, one on Voyager 2, both launched in 1977. Carl Sagan chaired the committee that assembled it. Frank Drake was the technical director and devised the scientific diagrams. Anne Druyan was the creative director. John Lomberg was the design director. Timothy Ferris produced it. What is on the record itself is well known, and I will not dwell on it. 115 images encoded as analog video. Greetings in 55 languages. The sounds of Earth, including surf, wind, thunder, birds, whales, a heartbeat, a kiss. And 90 minutes of music, from Bach to Chuck Berry, to a Navajo night chant, to a Bulgarian folk song. But the music is not the part that matters for what we are doing tonight. The part that matters is the cover. The record is protected by an aluminium cover, and etched into the outside of that cover is a set of diagrams that constitute one of the most carefully thought-through objects our species has ever produced. There are 4 things on it. The first is playback instructions. A drawing of the record with the stylus in its correct starting position and the rotation speed given in binary. Someone who has never seen a phonograph is told, in the most reduced form possible, what to do with the object. The second is the calibration standard, and this is the elegant part. The binary numbers on the cover mean nothing without a unit, and there is no unit 2 civilizations could agree on in advance. So the cover shows a diagram of the hydrogen atom undergoing its hyperfine transition, the flip of an electron's spin relative to the proton it orbits. That transition produces radiation at a wavelength of 21 centimeters and a frequency of 1,420 megahertz, and it has a period of 0.70 nanoseconds. Hydrogen is the most abundant substance in the universe, and that transition happens the same way everywhere. So the cover defines its own units in terms of a physical constant any technological species would already know, and then expresses every number on the plate as a multiple of it. The third is a map. 14 pulsars are drawn as lines radiating from a central point, with the length of each line indicating distance and the period of each pulsar written alongside it in binary. Pulsars are rapidly spinning neutron stars, and each one has a rotation period that is extremely precise and slightly, predictably different from every other. Locate 14 of them from their periods, and the central point of that diagram is unambiguously the Sun. And because pulsars slow at known rates, comparing their present periods against the ones on the plate also tells the finder when the object was launched. And the fourth is the detail that turns the golden record from a message into an archaeological object. In a circle about 2 centimeters across on the cover, there is an electroplated spot of ultra-pure uranium-238. Its activity is about 0.00026 microcuries, which is a very small amount of a very slow thing. Uranium-238 has a half-life of 4.468 billion years, which is very nearly the current age of the Earth. Anyone who finds that record can measure the ratio of the remaining uranium to its decay products and read off, directly from the object, how long it has been traveling. It is a clock. It was built to run for longer than the planet that made it has existed. And it was put there in 1977 by a committee working to a deadline on a modest budget, who had no realistic expectation that the record would ever be found by anyone. I want to stay with that for a moment, because I think it is the most quietly moving decision in the history of spaceflight, and it usually gets one line in the middle of a list. Sagan's committee had a few months. They had a budget that would not have covered a rounding error on the spacecraft itself. Everyone involved understood the actual probability that either Voyager would ever be intercepted by anything, and the probability is somewhere between very small and indistinguishable from zero. They knew that. And they included, on the cover, a means for the finder to date the object. Think about what that assumes. It assumes that the interval between sending and finding might be so long that the question of when would genuinely matter. Not decades, not centuries. Long enough that a finder holding the record would have no way to guess whether the makers were still alive or had been gone for 100 million years. The uranium spot exists because somebody sat in a room in 1977 and thought carefully about the confusion of a stranger who does not exist, and probably never will, and decided to spare them the trouble. That is care directed across a gap that may never be crossed, performed properly anyway. It is worth knowing about. How long the record itself stays readable is a question that gets quoted with more confidence than it deserves. The figures commonly given run from about 1 billion years up to several billion. Those are estimates, not measurements, and nobody has run the experiment. The limiting factor in interstellar space is cosmic ray damage accumulating in the surface of the disk, and it is slow, and the honest position is that we do not precisely know. There is a design decision about the golden record that gets very little attention and matters enormously for the purposes of this video. The records are not stored inside the spacecraft. They are mounted on the outside, in aluminium cases, bolted to the frame. That means the survival of the record does not depend on the survival of anything else. It does not need power. It does not need the spacecraft to hold together. Voyager 1's instruments will stop within the next few years as its plutonium supply falls below the threshold that keeps them warm, and eventually the whole vehicle will be a cold structure with nothing happening inside it. None of that touches the record. It is an independent object that happens to be attached to a machine, and when the machine is finished being a machine, the record simply carries on. That is, whether or not anyone planned it this way, the correct architecture for a deep-time artifact. Do not build a system. Build an object and let it ride. The fourth artifact is the strangest of the group because its intended recipient is us. Lagios 1, launched in 1976. It is not a spacecraft in any conventional sense. It is a brass sphere, 60 centimeters across, covered in 426 retroreflectors, and it does nothing. It has no power, no instruments, no transmitter, and no moving parts. Its entire function is to be a fixed point. Laser stations on the ground fire pulses at it and time the return, and by doing that continuously for decades, you can measure the drift of continents relative to one another with extraordinary precision. Because it needs to be a fixed point, it was placed in an orbit chosen to be extremely stable, high enough that atmospheric drag is nearly irrelevant. And that stability means its eventual fate is calculable. Lagios 1 will remain in orbit for about 8.4 million years, and then it will come down. Sealed inside the core of that sphere is a plaque. Sagan conceived it, and John Lomberg drew it. It has no words on it at all. What it has is 3 maps of the Earth, showing the arrangement of the continents at 3 different times. The first shows Pangaea, as the land was 268 million years ago. The second shows the continents as they were at launch in 1976. And the third shows where the continents are projected to be 8.4 million years from now. That third map is the delivery date. The plaque is addressed to whoever is standing on this planet when Lagios falls out of the sky, and the message is essentially this: here is when we sent it. Count the distance the ground has moved. Continental drift as a calendar. It is the only artifact on this list whose intended reader is a future inhabitant of the Earth, and it assumes, without stating it, that whoever opens it may not share a language, a species, or any part of a history with the people who sealed it. And the fifth may already be a ruin, in the most literal sense. On the 11th of April 2019, the Israeli lunar lander Bereshit failed during its descent and struck the surface of the moon at speed. It was a privately funded mission, and it very nearly worked. It was carrying a payload from the Arch Mission Foundation called the Lunar Library. 25 nickel discs, each 40 microns thick, holding roughly 30 million pages of material. The complete text of English Wikipedia, tens of thousands of books, linguistic keys. The encoding is the interesting part. It is not digital. The pages are stored as microscopic physical images at roughly the resolution limit of optical microscopy in a format the Foundation calls nanofiche. There is no file format to decode, no codec to reverse engineer, no machine required. There is a stack of metal foil with very small writing on it, and the only equipment needed to read it is a microscope, and the first few layers are deliberately readable at lower magnification so that a finder can work out that magnification is what is wanted. Nickel was chosen because it does not corrode, and because it is hard enough to survive an impact. The Foundation's own scientific team, examining orbital imagery of the crash site, believes the library survived. I want to be careful here. That is the Foundation's assessment. It has never been independently confirmed, nothing has been recovered, and no one has been back. Believed, not confirmed. But if it did survive, then somewhere in a small debris field on the near side of the moon, there is a stack of nickel foil containing a large fraction of everything our species has written down. And by the gardening numbers from the last part, it will still be there, within a meter of where it landed, in 100 million years. There is one more category worth adding to this list, and it is the only one still doing its job. The Apollo 11, 14, and 15 crews each left a retroreflector array on the lunar surface. These are simple things, panels of precisely cut corner cube prisms, and they have exactly one property. Light that hits them goes back the way it came, regardless of the angle it arrived at. Observatories on Earth fire laser pulses at those panels and time the return. And from that, we know the distance to the moon to within a few centimeters. And we know that it is receding from us at about 3.8 centimeters per year. Those arrays were installed between 1969 and 1971. They are still returning pulses today, more than 50 years later, with no maintenance, no power, and no moving parts. They are the longest continuously functioning objects human beings have ever placed anywhere off this planet, and they function because they were designed to do only one thing and to do it passively. Which is, again, exactly the lesson. The artifacts of ours that are still working are the ones with nothing to break. So let me put the 5 together, because the synthesis is the point of this part. We are a 300-year-old industrial civilization. We have no long-term plan. Our institutions rarely survive 2 centuries. Our data storage formats become unreadable within decades, and we routinely lose films, records, and archives from within living memory. By any reasonable assessment, we are not good at continuity. And yet, within 7 years of first putting anything above the atmosphere, we had produced 5 separate artifacts explicitly designed to outlive not just their makers, but their makers' species. 2 of them are designed to outlive the planet. Nobody decided this as policy. There was no program. It happened because a handful of people, on the side of much larger projects, thought it was worth doing and were allowed to. If that is simply what a young technological civilization does by default, almost as a reflex, then the deep time debris field of any older civilization should be substantial. Not monuments, not structures. Small, hard, deliberately inert objects scattered along whatever trajectories their makers happen to be flying, most of them going nowhere in particular. That is what we should be looking for. And that is a much more specific thing to search for than a signal. But there is another kind of trace, and it does not require anyone to have built anything at all. Some of what a civilization leaves is not an object you could pick up. It is written into the air of the planet it lived on. Part 5. The chemistry of a dead world. Everything in the last part required going somewhere. An object on a surface has to be found by something that travels to it, and across interstellar distance that is not a search anyone can currently run. There is a second category of remains, and it has the enormous advantage of announcing itself across light years without anyone having to move. It is the chemistry a civilization leaves in the air of its own planet. And there is a small, strange, entirely serious body of published work on what that chemistry would look like after everybody had gone. The foundational paper appeared in 2014 from Henry Lin, Gonzalo González Abad, and Abraham Loeb at Harvard, under the title Detecting Industrial Pollution in the Atmospheres of Earth-like Exoplanets. The insight behind it is straightforward once you have heard it, and slightly unnerving afterwards. Biology and geology, between them, produce an enormous number of compounds, but not an unlimited number. There is a finite catalogue of molecules that living things and rocks and weather can make, and there are compounds that fall outside it entirely. Molecules that no natural process on any planet has ever been observed to produce, and that only appear when something builds a factory. Chlorofluorocarbons are the clearest case. They were manufactured in enormous quantity through the 20th century as refrigerants, as aerosol propellants, as solvents. They are the compounds that opened the hole in the ozone layer. And they have no natural source whatsoever. Not from volcanism, not from biology, not from any chemistry that happens on its own. Every chlorofluorocarbon molecule in the atmosphere of this planet was made in a plant by somebody. Lin and his colleagues identified the 2 most detectable candidates, tetrafluoromethane and trichlorofluoromethane, the compound usually referred to as CFC11. Both have strong absorption features in exactly the infrared range the James Webb Space Telescope was built to observe. Their proposed target architecture is elegant and slightly grim, and it is worth walking through because it explains why this is possible at all. The difficulty with reading the atmosphere of a small rocky planet is contrast. When a planet passes in front of its star, a thin sliver of starlight filters through the planet's atmosphere on its way to us, and the molecules in that atmosphere absorb at their characteristic wavelengths. That is how atmospheric composition is measured. But an Earth-sized planet crossing a Sun-sized star blocks about 1/10,000th of the light, and the atmospheric sliver is a tiny fraction of that. The signal is minute. So Lin's team proposed looking at Earth-sized planets transiting white dwarfs instead. A white dwarf is the exposed, cooling core of a star that has already died. At around 6,000 Kelvin, its spectrum is close to the Sun's, so the light is familiar. But the star itself is roughly the size of the Earth. A planet the size of Earth crossing a star the size of Earth does not block a 10,000th of the light. It blocks a substantial fraction of it, and the atmospheric signal becomes enormous. Their calculation was that about 1.7 days of integration time would detect or rule out tetrafluoromethane, and about 1.2 days for CFC11 at concentrations 10 times current terrestrial levels. Not a decade of observing, days. There is something appropriate about the fact that the proposed method for finding the chemistry of a living civilization involves watching it silhouetted against the corpse of a star. But here is the part that makes this archaeology rather than surveying, and it is the reason this paper sits in the middle of this video. The two molecules have wildly different atmospheric lifetimes. CFC11 breaks down in roughly a century. Tetrafluoromethane persists for something on the order of 50,000 years. Across the whole family of chlorofluorocarbons, the lifetimes span from about 10 years at one end to something like 100,000 at the other. That difference is a clock. If you detect both the short-lived compounds and the long-lived ones, you are looking at a civilization that is producing them now. The factories are running. Somebody is home. If you detect only the long-lived compounds and the short-lived ones are absent, you are looking at the chemical residue of a civilization that stopped. The fast molecules have already broken down. The slow ones have not had time to. And the ratio between what remains and what has gone tells you, approximately, how long ago the production ended. That is a dating method for an extinct civilization, derived from first principles, using an instrument that is already in orbit, already operating, and already looking at exoplanet atmospheres for entirely different reasons. Let me take that idea somewhere it has not been taken, and be clear that this next stretch is imagination sitting on top of the physics we have just established. Picture the observation. Not the discovery, the observation, because the two are separated by about 2 years, and most of the interesting part is in the gap. A rocky planet, roughly Earth-sized, crossing the face of a white dwarf a few hundred light-years from here. The transit takes about 90 seconds. In that 90 seconds, starlight from a dead star passes through the upper atmosphere of a small world and arrives, very slightly altered, at a mirror in orbit around a point beyond the moon. The alteration is not visible to anyone. It is a set of dips in a curve, at wavelengths that mean nothing to the eye. The instrument records them, and the data goes into a queue. And in the spectrum, when someone finally works through it, there is tetrafluoromethane. Not a trace. A quantity that requires industry. And there is no CFC11. None. Below the detection limit, and the detection limit is good. That absence is the whole story. The short-lived compounds are gone, and the long-lived ones remain, and the ratio between them is a number, and the number converts to a duration. Somewhere between 40 and 80,000 years ago, on that planet, the last factory stopped. Imagine holding that. Not a signal, because there is nobody to send one. Not a ruin you could photograph, because at that distance, a continent is smaller than a pixel, and always will be. Just a molecule that lasts 50,000 years, still hanging in the air above a surface where nothing has happened for a very long time, arriving here as a shallow notch in a curve. And the light carrying it left that planet before anyone on this one had thought to ask the question. Tetrafluoromethane is also produced as a byproduct of aluminium smelting, incidentally, which strengthens the case considerably. It is not a niche compound that only appears if a civilization happens to invent refrigeration. It falls out of basic industrial metallurgy, which any technological species doing anything at scale is likely to be doing. Chlorofluorocarbons are not the only compound on the list, incidentally, though they are the cleanest. Nitrogen dioxide has been proposed separately as a marker of industrial combustion. It is produced in quantity by burning things at high temperature. It has natural sources too, but the concentrations that industrial activity generates sit well above the natural background. In principle, it is detectable around nearby stars with a sufficiently large telescope, and it has the advantage of being a marker of a much earlier stage of industrialization than refrigerant chemistry. The difficulty running through all of this work is disentanglement. Oxygen in an atmosphere is a biosignature, because on this planet it is produced overwhelmingly by living things. Ozone is a biosignature for the same reason, being made out of oxygen. But there are non-biological roots to both, and separating a world with a biosphere from a world where ultraviolet light is splitting water apart is one of the central technical problems in the entire field. Technosignatures are, in one narrow sense, easier, precisely because there is no natural root at all. Nothing makes tetrafluoromethane by accident. Now, if that paper works out what the residue looks like, there is a second one that works out what the ending looks like, and it is one of the odder documents in the scientific literature. In 2016, Adam Stevens, Duncan Forgan, and Jack O'Malley James published in the International Journal of Astrobiology a study called Observational Signatures of Self-Destructive Civilizations. Their motivation was technical rather than morbid. The Drake equation, the standard framework for estimating how many communicating civilizations exist, ends in a term for how long a civilization lasts, and nobody has any handle on it at all. Stevens and his colleagues reasoned that if you could work out what each specific mode of ending looks like from a distance, then finding one would put a real constraint on that term. So they went through the possibilities and filtered them down to 4, and then catalogued the spectral consequences of each. The first is full nuclear exchange, and their finding here is unexpectedly deflating in a way that I think builds confidence in the rest of the paper. The gamma-ray flash from a planetary nuclear war would be completely undetectable at interstellar distance. They actually ran the numbers on the yield that would be required to see it, and it is far beyond any arsenal that has ever existed on this planet by an enormous margin. The idea that a civilization ending in fire would light up briefly in somebody's telescope is simply wrong. It would not. What would be visible, in principle, is the aftermath. Nuclear detonations drive nitrogen and oxygen together in the atmosphere, producing sharply elevated nitrogen oxides. There would be an enhanced green oxygen emission line at 558 nanometers, which is, as it happens, the same emission that produces the dominant color in the auroras on this planet. Anyone who has seen a photograph of the northern lights has seen that exact spectral feature. And there would be raised electron density in the ionosphere. And then the paper delivers the detail that stays with you. The same event produces nuclear winter, and nuclear winter means dust and soot lofted into the upper atmosphere, and dust and soot increase atmospheric opacity. The obscuring layer settles over the very markers that would have identified what happened. A civilization that destroys itself by fire draws a curtain across the evidence as part of the same event. It would not go out with a flash. It would go out by becoming harder to see. The second mode is biological. An engineered agent that killed the biosphere, or a large part of it, would produce mass death and then mass anaerobic decay. Decay without oxygen produces methane and ethane, and both are detectable in an atmosphere. So a world that had been sterilized biologically would show a distinctive spike in exactly those two gases, sustained for as long as the decomposition ran. The third mode is the runaway self-replicator, the scenario in which manufacturing machinery designed to build copies of itself is not adequately constrained and converts the available material of the biosphere into more of itself. The idea was described by Eric Drexler in 1986, and it has been argued about ever since. Whatever one thinks of its plausibility, Stevens and his colleagues note that it would produce a thermal and spectral signature quite distinct from a nuclear one, because the endpoint is a planet whose surface composition has been fundamentally altered rather than merely burned. The fourth mode is pollution, and they divide it into three. Pollution of the star itself, meaning enough material dumped into the star's convective zone to shift its measured surface composition. They judge this a poor marker, and the reason is arithmetic. You would need something on the order of 10 Earth masses of material to move a star's metallicity measurably. That is not pollution. That is dismantling a solar system. Pollution of the planet, where they defer explicitly to Lin's chlorofluorocarbon work, which we have already covered. And pollution of the orbital environment. This is the debris cascade that Donald Kessler described in 1978, in which collisions between objects in orbit produce fragments, and those fragments cause further collisions, until a planet is surrounded by a shell of high-velocity debris that makes its own orbital space permanently unusable. It is not a hypothetical concern. It is a live engineering problem in Earth orbit right now. The orbital debris case deserves a little more than a passing mention, because it is the one mode of self-limitation on that list that is unfolding right now and that anyone can verify. Donald Kessler's argument, published in 1978 while he was working at NASA, is a piece of straightforward collision arithmetic. Objects in low Earth orbit travel at around 7.8 kilometers per second. When two of them meet, they do not bump. They disintegrate, and each collision converts two trackable objects into thousands of untrackable fragments, each carrying the same enormous speed. Those fragments then raise the collision probability for everything else at that altitude. Past a certain density, the process becomes self-sustaining. Collisions generate the debris that causes the next collisions, and the population grows without any further launches at all. The end state is a shell of high-velocity fragments surrounding the planet, through which nothing can safely pass. What makes it relevant to this video is the permanence. At low altitudes, atmospheric drag eventually clears debris, over years to decades. Higher up there is effectively no drag, and a fragment released at 2,000 kilometers will still be there, at the same speed, in 10,000 years. A civilization that lost control of its own orbital environment would not merely lose access to space. It would leave behind a structure, a thin, fast, permanent shell of manufactured metal that would outlast almost everything on the surface below it, and that would be, from a distance, one of the more detectable things about the whole planet. It is an odd sort of monument, but by the standards of this video, it is exactly the right shape. Small, hard, metallic, in vacuum, going nowhere, and lasting. Their overall summary is that the different signatures decay on very different timescales. Some fade faster than a civilization's own communication lifetime, meaning you would have to be looking almost immediately. Others persist for thousands of years, which means the detectability of an extinction depends entirely on how it happened, and some ways of ending are simply invisible from outside. The value of this part is not that any of this has been detected. None of it has. There is no candidate. Nobody has found a nitrogen oxide anomaly, or an unexplained methane spike, or a long-lived fluorocarbon around another star. The value is that the question has moved out of speculation and into instrument specifications. Somebody has sat down and calculated the integration time in days. Somebody else has tabulated the spectral consequences of 4 different ways for a civilization to end, with wavelengths attached. That is what it looks like when a field stops treating extinction as a metaphor and starts treating it as an observable. And it means that if the residue of a dead world is sitting in the data somewhere, we now know which lines to check. I will close this part on the obvious observation, and I want to make it calmly, because it is a fact rather than a warning. Every marker described in this part is one we can currently produce. The chlorofluorocarbons in Lin's paper were in the atmosphere of this planet in measurable quantity for decades before they were regulated, and the long-lived ones are still there and will be for a long time. The The Montreal Protocol of 1987 is the reason the short-lived ones are now falling, which means our own ratio between fast and slow molecules is already shifting and would already be readable from outside as a change in industrial behavior. The debris shell is accumulating. The nitrogen isotopes have moved. If somebody 30 light-years away had our instruments and pointed them at this planet, the signature they would find is the one described in this part. Not as a prediction, as a current measurement. All of that, though, still involves looking outward at something very far away. And some of the oldest material in this galaxy does not require us to look anywhere at all because it comes here on its own. Part 6. The oldest things that come to us. Everything so far has required us to go somewhere, or to look somewhere very far away. This part is about the material that arrives here on its own, without anybody sending it, and about the fact that some of it is older than the Sun and has been sitting in laboratory drawers for decades. Start with a morning in 1969 in a farming district in Victoria, Australia. On the 28th of September that year, a fireball came in over the town of Murchison, north of Melbourne. It broke apart in the atmosphere and scattered fragments across the district, into paddocks and yards and along roads. People collected them. In total, something over 100 kilograms was recovered, which is a large fall by any standard. The Murchison meteorite is a carbonaceous chondrite, which is the most useful kind of rock that falls out of the sky. Chondrites are primitive. They have never been melted, never been part of a planet, never been reprocessed by heat or pressure or geology. They are, essentially, the original material of the solar system, assembled at the beginning and left alone since. Murchison, in particular, is rich in carbon and in water-bearing minerals, and it contains more than 90 amino acids, most of which do not occur in terrestrial biology at all, which is itself a substantial fact. The chemistry that precedes life is manufactured in space and delivered, rather than being invented on planets. But that is not why Murchison is in this video. Inside that rock, mixed into the matrix, there are grains that did not come from this solar system at all. They are called pre-solar grains. They are microscopic pieces of extremely durable minerals, mostly silicon carbide, that condensed in the outflowing atmospheres of stars that died before the Sun existed. When a star reaches the end of its life and begins shedding its outer layers, the material cools as it expands, and in that cooling gas, certain refractory compounds condense into solid grains, in the same way that soot condenses in smoke. Those grains are then blown out into interstellar space, and then they drift. For hundreds of millions of years, sometimes for billions, alone in the space between stars. Until eventually one of them is caught up in a collapsing cloud of gas and dust, and incorporated into a new solar system, and locked inside a rock that never gets hot enough to destroy it. They are rare. Pre-solar grains are found in only about 5% of meteorite falls. And they are tiny. Something like 100 of the largest of them would fit inside a printed full stop. In January 2020, Philip Heck of the Field Museum of Natural History and the University of Chicago, working with colleagues at ETH Zurich and in Australia, published ages for 40 of them. The method is a stopwatch that runs on cosmic rays, and it is very clever. While a grain is drifting unprotected through interstellar space, galactic cosmic rays penetrate it and collide with atomic nuclei inside, producing new isotopes at a rate that is reasonably well known. The longer the grain floats alone, the more of those isotopes accumulate. Measure the accumulation, and you measure the exposure time. Not when the grain formed exactly, but how long it spent drifting before something collected it, which combined with the age of the solar system gives you an age for the grain. The results run from about 4.6 billion years to roughly 7 billion. Most of them cluster between 4.6 and 4.9 billion. A minority, around 8%, exceed 5.5. The oldest are somewhere around 7 billion years old. I want to be careful with those numbers because the version that traveled around the world was compressed into 5 to 7 billion years, and that is press shorthand rather than what the measurements say. Most of these grains formed between 4.6 and 4.9 billion years ago. Some of them are around 7 billion years old. All of them predate the Sun. They are the oldest solid material ever dated on this planet. There is a further layer to what these grains can tell us, and it goes beyond age. Each one carries an isotopic fingerprint, and that fingerprint identifies the kind of star that made it. Different stellar processes produce different ratios of the same elements. A star fusing hydrogen through one pathway leaves a different signature in its ejected carbon than a star using another. So when a laboratory measures the isotopic composition of a single pre-solar grain, it is reading a description of the star that manufactured it, written into a particle far too small to see. Most of the silicon carbide grains in Murchison came from asymptotic giant branch stars, which are stars in the late, unstable phase of their lives, swelling and pulsing and shedding their outer layers into space. A smaller number carry the fingerprints of supernovae, which means the drawer in Chicago contains a small, sorted collection of samples from individual named categories of dead star, each one identifiable, each one having been somewhere specific. Nobody knows which stars. There is no way to trace a grain back to a particular object across 7 billion years and an unknown path through the galaxy. But the grains are individual objects from individual stars, and they are here, and we have them. And there is a detail about how the result happened that I find as interesting as the result. Those grains were separated out of Murchison fragments at the University of Chicago more than 30 years before the dating technique existed. Somebody isolated them, catalogued them, put them in storage, and left them there. The measurement in 2020 was possible only because a laboratory had preserved a set of samples for 3 decades with no immediate use for them and no way to know what they would eventually be for. Let me put you in that field on the morning of the fall, because the scale of what was happening is worth feeling rather than being told. It is a Sunday morning in late September, early spring in southern Australia. The light is ordinary and the air is cool. At about 11:15, a bright object appears in the sky over the district, and it is bright enough to be seen easily in full daylight. It breaks into 3 pieces as it comes down and leaves a smoke trail behind it that hangs in the air for several minutes. And then, some seconds later, the sound arrives, because sound is slow and light is not. A long rolling detonation, felt as much as heard, rattling windows across the district. People go outside. They stand in yards and driveways and look at the trail. Some of them find stones, warm to the touch, sitting in paddocks and on roads, and in one case, going through the roof of a hay shed. They are dark, crusted black on the outside where the atmosphere burned them, and they smell strongly of methylated spirits, which is a genuine and well-documented feature of that particular fall. Now hold one of them and narrow the focus. Through the fusion crust, into the grey matrix. Past the chondrules, the small round beads that formed as molten droplets in the disk around the young sun and cooled before there were any planets. Down past those, into the fine material between them. And there, somewhere in the matrix of the stone in your hand, is a grain of silicon carbide, perhaps 1/100th of the width of a human hair. That grain condensed in the cooling outflow of a dying star 7 billion years ago. It has never been inside a planet. It has never been melted. For billions of years it drifted through interstellar space, alone, while the gas that would become the sun was still an undisturbed cloud somewhere else entirely. It was swept up into the collapse that made this solar system, and it has been locked inside a rock ever since. And this morning it came down into a paddock in Victoria and stopped moving for the first time in 7 billion years. It sat in a drawer in Chicago for 30 years before anyone could tell how old it was. It is worth pausing on how strange the recovery itself was. Meteorite falls are not usually collected. Most of them land in oceans, which cover most of the planet, and most of the remainder land somewhere nobody is looking. The ones that are recovered because they happen to come down over inhabited ground in daylight, with people outside to see them. Murchison came down over farmland on a Sunday morning in front of witnesses, and the local community collected it, and it was distributed to institutions within weeks. Had that fireball arrived 6 hours earlier, or 400 kilometers to the south, the oldest solid material ever dated on this planet would be at the bottom of the Southern Ocean, and nobody would know it had ever existed. Which is a useful thing to hold on to for the rest of this video. The archive is enormous, and it is arriving continuously, and our sampling of it is almost entirely a matter of where people happen to be standing. Now the framing turn, because this is where the part earns its place in the video. If material from other star systems arrives here routinely, embedded in rocks that fall out of the sky and land in farmland, then this galaxy is not sealed. It is not a set of isolated systems with nothing passing between them. Matter circulates. It has always circulated. Anything that entered that circulation anywhere at any point in the last 13 billion years would eventually arrive somewhere, and some fraction of it would arrive here. Which brings us to the visitors. 3 objects have now been confirmed to have entered this solar system from outside it. 3 out of everything that has ever been catalogued. The first was found by the Pan-STARRS survey on the 19th of October 2017 and named One-Eye Oumuamua. Its orbit was hyperbolic, meaning it was not bound to the Sun and had not come from here. It was small, apparently elongated, and it showed a slight acceleration that could not be accounted for by gravity alone, without any visible dust tail to explain it. That anomaly drove several years of argument. The mainstream reading, which has held, is outgassing of a volatile that produced no visible dust. It left, and nobody will ever get a closer look at it. The second was found by one man with a telescope he made himself. On the 30th of August 2019, Gennady Borisov was observing from his own site at Nauchnish in Crimea, using a 65-centimeter telescope that he had designed and built with his own hands. He worked as a telescope engineer at the Crimean Astrophysical Observatory, and he hunted comets as an amateur in his own time, on his own equipment. He found a faint object with a short dust tail, about 3 astronomical units from the Sun, moving on a path that did not look right. Over the following week, follow-up observations by amateurs and professionals across the world established that the orbit was hyperbolic. It was the second interstellar object ever identified, and the first confirmed interstellar comet. I want to hold on that for a moment, because it is worth more than the sentence it usually gets. At the time, there were multiple automated survey programs running on this planet, funded and staffed and using instruments far larger than his, and their explicit purpose was to find exactly this kind of object. They had been trying. They had found the first one, by luck, on its way out. The second interstellar object ever seen, and the first one caught while it was still coming in, was found by a man working alone, in his own time, at a site he built, with a telescope he ground and assembled himself. Borisov was not a beginner, incidentally, and the story is better for that. Two-Eye Borisov is the 7th object to carry his name. He had been finding comets from that site for years, methodically, on equipment of his own construction, in the hours available to a man with a full-time job at an observatory. The discovery was not a piece of luck that happened to an outsider. It was the outcome of a long, patient, unglamorous practice, finally intersecting with something extraordinary. The archive is open. That is the thing to take from it. The material has been arriving here for 4.5 billion years, and it keeps arriving, and the record of it is available to anyone patient enough to keep watching the same piece of sky. And then there is the third one, which is the reason this part is where it is in the video. 3I/Atlas was found on the 1st of July 2025 by the Atlas Survey Telescope at Rio Hurtado in Chile. Matthew Hopkins and colleagues at Oxford analyzed its trajectory against a model of the galaxy's stellar populations and reached a conclusion that belongs at the center of everything we have been building tonight. It is the first known interstellar object to come from the Milky Way's thick disk. The thick disk is the older population of stars in this galaxy. They sit above and below the thin plane where most star formation happens now. They move on hotter and more inclined orbits, and they are old. If 3I/Atlas formed around a thick disk star, then it formed a very long time ago. Their estimate is that it may be more than 7 billion years old. That would make it more than 3 billion years older than the Sun, and the oldest comet ever observed by anybody. Its recent history is worth giving, because it grounds all of this in the present rather than the abstract. It reached its closest approach to the Sun at the end of October 2025, passing about 1.36 astronomical units out, between the orbits of Earth and Mars. It did not break up, which was a live possibility. Observations in December found it far more active after perihelion than before, its ices sublimating fully as the heat worked through it. Measurements in January of this year found a surprisingly low ratio of carbon dioxide to water, meaning its composition shifted as it warmed. It passed Jupiter in March, at about 53 million kilometers. And it is now outbound and fading, on a near-symmetric exit, leaving this system for good. Two further things about 3I/Atlas are worth adding, because they change the scale of what happened. The first is size. The nucleus is still debated, but estimates run as high as about 10 kilometers across, which would make it perhaps 10 times larger than 2I Borisov. That is not a pebble. That is a body comparable in size to the object that ended the Cretaceous, arriving from another star system, passing between the orbits of Earth and Mars. The second is what it implies about the traffic. 3 confirmed interstellar objects in 9 years is not the rate at which they arrive. It is the rate at which we have been capable of noticing them. Population estimates suggest a significant number are passing through the inner solar system at any given moment, and that the overwhelming majority are too small, too dark, and too fast for the instruments that existed before this year to catch. We have not been watching an empty road. We have been watching a busy one with our eyes almost closed. There is a mission concept for chasing one down. It is called Project Lyra, and it has been studied in reasonable technical detail, and it is unfunded. The core difficulty is timing. Interstellar objects are typically identified after their closest approach, already accelerating away, and a spacecraft launched in response would need an enormous velocity budget to catch something that is leaving at tens of kilometers per second and not slowing down. To do it properly, you would need to know an object was coming before it arrived, which requires a survey capable of finding faint moving objects across the whole sky, repeatedly, every few nights. Hold that requirement in mind. We will come back to it. So here is where that leaves us. A body that formed around a star which died before this planet existed came through our solar system last year. Every major observatory on Earth looked at it. We measured its composition, watched its chemistry change as it heated, tracked it past Jupiter, and are now watching it go. It carried no message. Nobody built it. It is a lump of ancient ice and dust, and nothing more. But it demonstrates, physically and without any ambiguity, that objects from star systems billions of years older than ours arrive in this solar system, pass close enough to examine in detail, and can be studied with the instruments we already have. The delivery mechanism this entire video has been circling around is not hypothetical. It exists, it is running, and it has delivered 3 times in the last 9 years. Which raises the obvious question. If the galaxy is that open, and material has been moving through it for 13 billion years, why has it stayed so quiet? And the silence, it turns out, is a good deal more informative than it first appears. Part 7. The silence as a dig site. Everything up to this point has been method. Where to look, what survives, what arrives here on its own, what chemistry a dead world would leave in its air. This part is about the evidence we already have, which is the silence itself, and about what that silence actually tells us. The answer is more specific and considerably more interesting than the way the question is usually framed. The usual framing goes back to a lunch. In 1950, at Los Alamos, Enrico Fermi was eating with several colleagues, and the conversation had turned to flying saucers, which were in the newspapers at the time. The discussion moved on to other things, and then, some minutes later and apparently out of nowhere, Fermi asked a question that his companions remembered for the rest of their lives. Where is everybody? The point behind the question is arithmetic. The galaxy is 100,000 light-years across and 13.5 billion years old. Even at speeds well below light speed, crossing it takes a few million years at most, which is nothing against that age. So if anyone had ever set out, they should have arrived, everywhere, long ago. Michael Hart formalized the argument in 1975, and Frank Tipler sharpened it considerably in 1980 with a mechanical version that is harder to escape. Tipler's argument is about self-replication. Suppose a civilization builds a probe that can travel at even a small fraction of light speed and, on arriving at a new star system, can use local material to construct copies of itself, which then depart for further systems. That process is exponential. Run the numbers and the entire galaxy is visited within a few million years from a single starting point, using no physics we do not already understand. And once a system has been visited, the probes stay because there is no reason to remove them. Under that model, the absence of any such object in this solar system is not a mild puzzle. It requires an explanation. Although I want to flag the weak joint in that chain, because it is the softest part of the whole argument, and it is usually glossed over. Tipler's reasoning depends entirely on an assumption about what advanced civilizations want. It assumes that a species capable of building self-replicating probes would want to fill the galaxy with them. That is not a physical claim. It is a claim about motivation, projected across a gap we have no way to reason across, and every version of the Fermi argument inherits it. The classic survey of what the silence might mean predates almost every modern version of the argument. In 1983, David Brin published a paper simply called The Great Silence, and he did something nobody had done properly before. He gathered every proposed explanation that had been offered, sorted them, and assessed each one on its merits. The list is long. Perhaps interstellar travel is harder than it looks. Perhaps civilizations reliably destroy themselves. Perhaps they turn inward and stop expanding. Perhaps they are here, and we cannot recognize them. Perhaps they are deliberately staying quiet, or deliberately leaving us alone. Perhaps radio is a brief technology that everybody passes through in a century and abandons, so that the window in which any two civilizations are both using it is impossibly narrow. Brin's contribution was to point out that these are not competing theories in the ordinary sense, because most of them are unfalsifiable with current instruments, and because several could be true simultaneously in different places. The silence is compatible with almost everything, which is precisely what makes it such poor evidence for any particular conclusion. including the conclusion that there is nobody there. Robin Hanson gave the difficulty its modern name in 1996. The Great Filter. Somewhere in the long sequence of steps between ordinary chemistry and an interstellar civilization, there is at least one step that is very nearly impossible. Something that almost nothing gets past. The question that matters is not what the step is. It is whether it lies behind us or ahead of us. If the filter is behind us, then we are the improbable survivors of something almost nothing survives, and the road ahead is open. If the filter is ahead of us, then everything that ever got this far has run into it, and we will too. All of that is a question about the present tense. Where is everybody? But this video is not asking where everybody is. It is asking where everybody was. And that turns out to be a different equation, with a different answer, and someone has written it down. In 2016, Adam Frank at the University of Rochester and Woodruff Sullivan III at the University of Washington published a paper in the journal Astrobiology called A New Empirical Constraint on the Prevalence of Technological Species in the Universe. What they did is, I think, the single most important move in this entire subject, and it is almost embarrassingly simple once you see it. They took the Drake equation and deleted the last term. The Drake equation was written by Frank Drake in 1961, not as a predictive formula, but as an agenda for a meeting. It is a chain of factors multiplied together. The rate at which stars form, the fraction with planets, the number of habitable planets per system, the fraction where life begins, the fraction where intelligence arises, the fraction that develops communication, and finally, the length of time such a civilization remains detectable. Multiply them, and you get the number of civilizations broadcasting right now. That final term, the lifetime, is the problem. Every other factor in that equation has improved dramatically over the last 30 years. We now know from gravitational microlensing surveys that essentially all stars have planets. We know from the Kepler statistical census that roughly 1 in 5 has a planet in the habitable zone. Those were guesses in 1961, and they are measurements now. The lifetime term has not improved at all, and it cannot, because we have a sample size of 1, and we do not yet know how long we last. It is pure guesswork, and because the whole thing is a multiplication, that one unmeasurable factor dominates the answer. So Frank and Sullivan removed it. And in removing it, they changed the question from how many civilizations exist right now to how many have ever existed, anywhere in the observable universe, across all of time. They called their version the A form. A for archaeology. And they gave the question a name that could serve as the subtitle of this entire video. The Cosmic Archaeological Question. Here is the calculation, and it is worth walking through slowly because the numbers do the work. There are about 2 times 10 to the 22nd stars in the observable universe. 20,000 billion. Essentially all of them have planets. About 1 in 5 has a planet in the habitable zone. Multiply those and you get 4 times 10 to the 21st habitable zone planets that have existed within our view. Now the question. How unlikely does it have to be, per habitable planet, for a technological species to emerge in order for us to be the only one that has ever done it anywhere? Their answer is the number this video has been building toward. The probability would have to be smaller than about 1 in 10 to the 22nd. Their own stated pessimism line, the point at which you could rerun the entire history of the universe 100 times over and get a lone technological species only once, sits at 2.5 times 10 to the minus 24th. Their careful phrasing is this. Only if the probability falls somewhere between 1 in 10 to the 22nd and 1 in 10 to the 24th is it likely that no other technological species has ever arisen in the entire universe. That number needs context, because on its own it is just a lot of zeros. 1 in 10 to the 22nd is roughly the odds of walking onto a beach, reaching down, and picking up one specific grain of sand. Except not one beach. Every beach and every desert on this planet, all the sand there is, and finding the one grain, and then doing it again, several times over, to get down to the threshold they are describing. That is what we would have to believe about ourselves. Not that we are rare, not that we are unusual, that the emergence of technology is more improbable than nearly any process anyone has ever seriously proposed for anything. Sit with that for a moment, because it is the point in this video where the scale actually lands. There have been 4 times 10 to the 21st planets in the habitable zones of their stars, within the part of the universe we can see, across 13.8 billion years. And for us to be the first and the only, the thing that happened here would have to be a coincidence larger than almost any other quantity in science. The realization is not that we have company. Nobody has demonstrated that, and Frank and Sullivan do not claim it. The realization is the reverse. The assumption that we are alone, which most people carry around as the safe, modest, default position, turns out to be the extraordinary claim. It requires believing in a piece of luck so extreme that it is difficult to state without it sounding like a joke. They also give a version scaled to this galaxy alone, and it is easier to hold in your head. For the Milky Way, the threshold is 1.7 times 10 to the minus 11th, which means that if the chance of a habitable planet producing a technological species is better than about 1 in 60 billion, then it has almost certainly already happened here, in this galaxy, at some point during its 13.5 billion years. 1 in 60 billion. That is the bar for it having happened before, locally. Frank and Sullivan also give the intermediate scales, and they are useful because they show how quickly the numbers change with the size of the volume you are asking about. For a galaxy cluster, a group of perhaps 1,000 galaxies bound together by gravity, the threshold is 4 times 10 to the minus 14th. For a supercluster, the largest gravitationally influenced structures, it is 2 times 10 to the minus 15th. And for the whole observable universe, it drops to the figures we have just been through. Read that as a ladder. The larger the volume you ask about, the smaller the per-planet probability needs to be for something to have happened somewhere inside it. Which means the honest answer to whether anyone has ever existed depends enormously on how big a question you are willing to ask. Confined to this galaxy, the bar is 1 in 60 billion, and reasonable people can disagree about whether we clear it. Extended to everything we can see, the bar becomes so low that clearing it requires almost nothing at all. It is worth saying where those input numbers came from, because they are the reason this calculation is possible at all, and they did not exist a generation ago. The fraction of stars with planets comes from gravitational microlensing surveys, which detect planets by the way a foreground star's gravity briefly magnifies the light of a background one. The 1 in 5 figure for habitable zone planets comes from the statistical yield of the Kepler mission, which stared at a single patch of sky containing about 150,000 stars for 4 years and counted transits. Before Kepler, the second and third terms of the Drake equation were arguments. After Kepler, they were measurements with error bars. That is the change that made Frank and Sullivan's paper writable, and it happened within the last 15 years. Now, the honest counterweight, because this is not a settled question, and presenting it as one would be dishonest. In 2018, Anders Sandberg, Eric Drexler, and Toby Ord at the Future of Humanity Institute in Oxford circulated a paper called Dissolving the Fermi Paradox. I want to be clear about its status. It is a preprint. It was submitted to a journal, and it remained a preprint, and it should not be cited as a peer-reviewed publication. It is also, in my view, one of the more important things written on this subject, and its argument is statistical rather than astronomical. Their point is about how everybody uses the Drake equation. When you plug a single best guess number into each factor and multiply, you are quietly asserting that you are certain about each of those numbers. But nobody is certain. The honest uncertainty on some of those factors spans many orders of magnitude. And it turns out that multiplying uncertain quantities is not the same operation as multiplying their averages. Their demonstration of this is short, and it is devastating. Take 9 factors. Say each one is uniformly distributed somewhere between 0 and 0.2, which is an entirely reasonable expression of not knowing. Multiply the averages together in the conventional way, and the probability of an empty galaxy comes out at about 4 in 10 to the 44th. Effectively 0. Now run the actual distributions properly, sampling from each and multiplying, tens of thousands of times. The galaxy comes out empty about 21% of the time. The conventional method was wrong by more than 40 orders of magnitude. Not because anybody used bad inputs, but because the arithmetic itself was the wrong arithmetic. Their full result, using their own uncertainty priors, is that the median number of civilizations in this galaxy is about 0.32, while the mean is around 27 million. Those two numbers describe the same distribution. It is so lopsided that the average case and the typical case have essentially nothing to do with each other, which is exactly what you would expect from multiplying together quantities that are uncertain across many orders of magnitude. From that, they get a 52% probability that we are alone in this galaxy, and a 38% probability that we are alone in the entire observable universe. And when they update those figures on the observed fact of the silence, they rise to somewhere between 53 and 99.6% for the galaxy, and 39 to 85% for the observable universe, depending on which update model you accept. There is a further model that deserves a mention here, because it takes the timing question seriously, in a way most of this literature does not. From around 2021, Robin Hanson and colleagues developed what they call the Grabby Aliens model. The premise is that expansionist civilizations, ones that spread and visibly alter what they occupy, should be detectable across cosmological distances once they exist, because they grow at a substantial fraction of light speed and do not stop. If such civilizations exist, then the fact that we do not see any places a constraint not on how many there are, but on when they appear. The model works backward from our own existence to ask what distribution of appearance times would make our situation typical rather than freakish. And it produces a specific answer. We appear early, considerably earlier than the average habitable planet would be expected to produce anyone, which lands in a strange place relative to everything else in this part. Lineweaver says the typical Earth-like planet has a 1.8 billion year head start on us. Hanson's model says that relative to the civilizations that go on to fill things up, we are early. Both can be true, and the reconciliation is that most planets never produce anyone at all, so the average planet's age tells you very little about the average civilization's start date. That is the kind of tension the field currently lives in. Not a disagreement about facts. A disagreement about which population you are averaging over. So we have two carefully argued positions pointing in opposite directions, and I think the right thing to do is present both squarely rather than choosing between them. Frank and Sullivan say the odds against anyone ever having existed are so steep that accepting them requires believing in something close to a miracle. Sandberg and his colleagues say our uncertainty is so wide that being alone is entirely unremarkable. Both papers are careful work by serious people. And the Oxford authors add a caveat that deserves to be quoted in substance, because it is the correct posture for this entire subject. Their conclusion, they write, does not mean that we are alone. It is a statement about our state of knowledge rather than a new measurement. Which brings that phrase back around. the one from the second part of this video. The record is thin. We used it then for the geology of this planet. 3 centuries of industrial activity falling below the resolution of the rock. The oldest exposed land surface at 1.8 million years. Ocean sediment only surviving back to the Jurassic. Less than 1% of the surface urbanized, and the accessible sections of ancient rock orders of magnitude smaller than that. Now apply it outward. We have searched less than 1 part in 1,000 of this solar system at a resolution that would notice a 10-meter object. We have listened to a few thousand stars in a narrow slice of the radio spectrum for a few decades out of a few 100 billion. We have measured the atmospheres of a handful of planets, none of them properly Earth-like. We have caught 3 objects arriving from other star systems, and only because 2 of them happen to be bright enough. That is the archive. And we have been reading emptiness off it. The record of this galaxy is thinner than the record of the Earth, and the record of the Earth could not resolve 300 years of us. But there is one result in that Oxford paper that pulls hard in this video's direction, and it is the note to finish this part on, because it changes what the silence means. When they update their model on the observed silence, the probability mass does not distribute evenly across the terms. It shifts overwhelmingly onto one of them, and it is the first. The origin of life from chemistry. In their analysis, the median value for that term is reduced by a factor somewhere between 7 and 10 to the 37th. The median value for civilization lifetime, the last term, is reduced by a factor of 1 or 2. Their reading is that the hard step is most likely behind us. The filter is in the past. And they note, correctly and without softening it, that this does not imply our safety. But think about what it means for the question we are actually asking tonight. If the difficult part was getting started, then the civilizations that do get started are not especially rare, and they are not especially short-lived. Which means the universe should be scattered with the remains of the ones that started early. Not transmitting. Not visiting. Just there, in whatever form survives, in whatever places nothing disturbs. The silence is not evidence of absence. On the best available reading, it is evidence about timing, which is an argument on paper. And an argument on paper is one thing. It is worth looking at what has actually happened every single time something in the real data looked artificial. Part 8. The anomalies we investigated and closed. This part exists to keep the rest of the video honest, and I want to say plainly what it is before we start. Every case in this part is one where something appeared in the data that could reasonably have been artificial. Each one was taken seriously by professionals. Each one was investigated properly over a period of years. And each one was resolved. None of them was a cover-up. None of them was suppressed. In every case, the answer was published. And in every case, the answer turned out to be more interesting than the mystery. If you want to know whether the search described in the last 7 parts is a serious enterprise or a hopeful one, this is where you find out. Because the way a field handles the things that turn out to be nothing is the only evidence you will ever get about how it would handle something that turned out to be real. The first case is the object that turned out to be ours. On the 3rd of September 2002, an amateur astronomer named Bill Young, observing from his own Desert Eagle Observatory at Benson in Arizona, picked up a small moving object. It was catalogued as J002E3. Young was not a novice. He had already discovered dozens of asteroids from that site. What made this one immediately strange was its orbit. It was not orbiting the Sun. It was orbiting the Earth. That should not happen. The Earth has one natural satellite, and it has had one for 4.5 billion years. Capturing an asteroid into a stable orbit around a planet requires a very specific combination of approach speed and geometry, and it is rare enough that at the time there were no confirmed examples. And this object's orbit was high and unstable and had the characteristics of something that had been captured recently rather than something that had been there a long time. So people looked properly. Two separate teams took spectra, which is the standard way of establishing what a small body is made of. Richard Binzel and Andrew Rivkin at the Massachusetts Institute of Technology used NASA's infrared telescope facility on Mauna Kea. Carl Hergenrother and Rob Whiteley at the University of Arizona observed invisible light at Steward Observatory. The spectrum did not match any asteroid class. Asteroids come in a manageable number of compositional families, and each family has a characteristic reflectance signature, and this object was not in any of them. What the spectrum did match was a combination of white paint, black paint, and aluminium. And in the near-infrared specifically, the absorption features matched titanium dioxide pigment, which is the white paint NASA used on the Saturn V. J002E3 was the third stage of Apollo 12. Launched in November 1969, it was supposed to end up in solar orbit after the mission, but the disposal maneuver left it too close to the Earth. It drifted around, escaped Earth's neighborhood in 1971, spent 3 decades in a heliocentric orbit, and then came back and was recaptured. It left again in June 2003. The cycle appears to be roughly 40 years, which means it will return. Now hold what actually happened there, because it is a working proof of the entire method this video has been describing. We built an object. We lost track of it. 31 years later, we found it again, and we could not identify it from its orbit, because the orbit had been perturbed too many times to trace backward. So instead we determined what it was by reading the chemistry of the paint on its surface from a distance using a telescope. That is archaeology. Applied to a manufactured object, at range, successfully, on our own hardware, by people who did not know in advance what they were looking at. The technique works. We have run it, and it produced the right answer. There is a broader point buried in that story, about how much of our own hardware is out there unaccounted for. Between 1957 and today, human beings have launched several thousand upper stages, and a substantial number of them were never tracked to a final disposal. Some fell back. Some were deliberately sent into the sun or into the Earth. And some, like Apollo 12's third stage, ended up in loosely bound orbits that nobody was maintaining a record of, drifting between heliocentric and geocentric capture over decades. Which means that when a survey finds a faint object on a strange orbit near the Earth, the first hypothesis is not an asteroid, and it is certainly not anything more exotic. The first hypothesis is that it is a piece of the 20th century that we mislaid. That has happened more than once. It will keep happening. And each time it does, the identification is made the same way it was made in 2002, by looking at what the surface is made of. We have, without ever intending to, built up a body of practical experience in the archaeological identification of manufactured objects in space. It exists because we are untidy. The second case ran for 17 years, and its solution is the funniest thing in modern radio astronomy. The Parkes Radio Telescope in Australia, a 64-meter dish in a sheep paddock in New South Wales, has been operating since 1961. Going back through its archival data to the earliest records in 1998, there are occasional bursts that look very much like fast radio bursts. Brief, bright, broadband, sweeping across frequency in the way a genuine signal from a great distance does. They were recognized as a distinct class and named peritons by Sarah Burke-Spolor and colleagues in 2011 during her doctoral work. Roughly 11 of them turned up in the archive. What made them puzzling was a contradiction in their properties. They appeared to come from all over the sky, which no astrophysical population does in that pattern. But they showed the frequency sweep that is the signature of a real signal having traveled through the ionized material between stars, which is exactly what should not be forgeable. The answer arrived in 2015. Emily Petroff, then at Swinburne University of Technology, and her colleagues published it after 3 peritons were detected in a single week in January of that year, which finally gave them enough live events to chase. Alongside the peritons, the team noticed strong out-of-band emission at 2.3 to 2.5 gigahertz. They tracked it to the microwave ovens in the observatory buildings. But the mechanism is the part that makes this story worth telling, because the ovens are not simply leaking. A microwave oven running normally produces nothing the telescope can see. A periton is produced only when somebody opens the door before the cycle has finished. The magnetron shuts down mid-operation, and in the fraction of a second it takes to power down, it emits a brief burst that sweeps across frequency as it dies. And the telescope only registers it when the dish happens to be at the right relative angle to the building. 17 years of an unexplained astronomical phenomenon, and it was the staff kitchen, and only when somebody was impatient about their lunch. There is an important corollary, and Petroff's team established it in the same paper. The ovens could not account for the genuine fast radio bursts. Those are real. They are astrophysical, they come from enormous distances, and one of the biggest open questions in astronomy sits on top of them. The peritons were interference sitting alongside a real phenomenon, and separating the two required exactly the patient, unglamorous elimination that any genuine technosignature claim would have to survive. It is worth appreciating the difficulty of what Burke-Spolor was up against, because the peritons were not obviously fake, and dismissing them would have been the wrong call. The frequency sweep is the key. When a genuine radio burst travels through the ionized gas between stars, the lower frequencies are slowed slightly more than the higher ones, so the pulse arrives smeared across time with the high frequencies first. The amount of smearing tells you how much material the signal passed through, which tells you roughly how far it came. It is one of the more reliable measurements in radio astronomy, and it is very hard to fake by accident. The peritons had that sweep. Not a perfect one, and the details were slightly off in ways that troubled people, but enough to look like something that had genuinely traveled. That is why the mystery lasted. The obvious answer, that they were local interference, appeared to be ruled out by the physics of the signal itself. And the resolution was that a magnetron powering down happens to produce a frequency sweep too, for entirely unrelated reasons, and it happens to land in roughly the right range. 2 completely different processes producing a similar-looking curve, which is, when you think about it, the exact failure mode this whole video has been warning about since the second part, where a natural warming event and an industrial one leave the same fingerprint in rock. The third case is the closest anyone has come, and it is the most instructive of all because of how the community handled it. In late April 2019, Breakthrough Listen was using the Parkes 64-meter dish to observe Proxima Centauri, the nearest star to the Sun. In the data was a narrow-band signal at 982.002 MHz. It drifted at 0.038 Hz per second. It was present across about 2.5 hours of observation. And it appeared only when the telescope was pointed at Proxima, disappearing when the dish moved off target. It was designated Breakthrough Listen Candidate 1. Everything about it looked right, and it is worth being specific about why, because the 3 properties together are close to a textbook description of what everyone has been looking for since 1960. It was narrowband. Nature is generally bad at producing narrowband radio emission. Astrophysical processes tend to be broad because they involve enormous numbers of particles doing slightly different things. A signal confined to a very narrow slice of the spectrum is the signature of a transmitter. It drifted. The frequency changed slowly and steadily over the observation, which is exactly what you would expect from a transmitter sitting on the surface of a rotating planet, its motion relative to us changing as the planet turns. And it was there when the telescope looked at Proxima, and gone when it looked away. That is the single most important check in radio astronomy, and it is the one that eliminates almost everything. It took 2 years of work to resolve it, and 2 papers appeared in October 2021. One came from the team that found it. The other was led by Sophia Sheikh, and its purpose was to build, from this case, a formal framework for verifying any technosignature claim. The conclusion was that the signal was an electronically drifting intermodulation product of local human transmitters. Intermodulation occurs when 2 or more signals mix in a piece of electronics and produce new frequencies that were not present in either original. Somewhere in the local radio environment, ordinary human equipment was producing a product at that frequency, and its behavior happened to align with the observing pattern in a way that mimicked an on-source detection. So the most compelling candidate in the history of the field was human radio equipment. But I want to be careful about how that lands, because the deflating reading of it is the wrong one. Breakthrough Listen made the raw data public, which is why independent verification was possible at all. The process took 2 years and nobody announced anything prematurely. And Sheikh's verification framework has since been applied to subsequent candidates and is now standard practice in the field. The case produced a permanent improvement in the discipline's ability to tell the difference. That is a better outcome than a mystery. One more thing about the Proxima case is worth noting, because it says something about how the announcement happened. The signal was detected in April 2019. It became public in December 2020, and it became public through a leak to the press, rather than through the team's own announcement. The papers did not appear until October 2021. So for the better part of a year, a signal that had already been substantially undermined internally was being discussed publicly as a possible detection, because the process of proving it wrong was slower than the process of talking about it. That gap is the practical problem the field actually has. Not secrecy. The opposite. Verification takes years, and public attention takes hours, and there is no procedure that can reconcile those 2 timescales. Whatever else a genuine detection would involve, it would involve a long period in which the people who knew the most were the least willing to say anything, and that reticence would be read by a great many people as concealment. The 4th case is short, and it is here because it shows how fast a story can outrun the evidence. In late July 2019, during its 8th lunar day, China's Yutu-2 rover was working across the floor of von Karman crater on the far side of the Moon. A member of the drive team noticed something unusual in a small crater along the route. The rover was redirected to examine it. A Chinese outreach publication described the material using a phrase that translated into English as gel-like, and that translation traveled around the world within days. Speculation followed immediately, as it always does. It was a translation artifact. The original phrase conveys something closer to glassy or vitreous, which is exactly what the material turned out to be. Follow-up analysis was published in 2020 by Gu Sheng and colleagues, using the rover's panoramic and hazard avoidance cameras, together with its visible and near-infrared spectrometer, and applying spectral unmixing to separate the components. The material is a dark greenish impact melt breccia, roughly 52 by 16 centimeters. It is regolith that has been welded, cemented and glassed together by the heat of an impact, and it contains plagioclase, iron magnesium silicate, olivine and pyroxene. Its closest analogues are 2 specific Apollo samples. Von Karman sits inside the South Pole Aitken Basin, which is the largest and oldest confirmed impact structure on the Moon. Impact melt is abundant there. The rover found exactly the kind of rock that region should be full of, and for about a fortnight, it was an international story. There is one further thing the U22 episode illustrates, and it is not about the Moon. The rover found the material, the drive team flagged it, the rover was rerouted, the spectrometer was pointed at it, and a result was published within about a year. That is a fast, correct, entirely ordinary piece of remote field geology, executed on the far side of the Moon by a vehicle being commanded through a relay satellite parked beyond it, because there is no direct line of sight to that hemisphere from Earth at all. None of that was reported. What was reported was a mistranslated adjective. And the reason is that the actual story required knowing what impact melt breccia is, and the mistranslation did not require knowing anything. That asymmetry is permanent, and it will apply to whatever gets found next. A real result in this field will arrive as a spectrum, or a set of orbital elements, or a ratio between two molecules. It will be unglamorous on its face, and it will need explaining. And it will be competing, from the moment it exists, against a version of itself that is easier to say. So let me put the four together, because the pattern is the point of this part. 4 anomalies. 4 investigations. 4 resolutions. Our own rocket stage, identified by its paint. A microwave oven. Terrestrial radio interference. And a rock. Not one of them was a cover-up. Not one of them was resolved in less than a year, and one took 17. And every single one of them produced a technique or a piece of infrastructure that makes the next investigation better. The paint spectroscopy of J002E3 is now routine for identifying artificial objects in orbit. The Periton work sharpened the separation of interference from real transient astronomy. Shake's framework is now the standard verification procedure. Even the U22 case improved the pipeline for spectral analysis on a rover. This is what a field looks like when it is doing the work properly. Slowly, publicly, with the boring answer published as prominently as the exciting question. And it is precisely why the cases that remain open are worth taking seriously. Not because mysteries are exciting, but because this field keeps solving the ones that can be solved, and it publishes the solutions, and it does not protect its own hypotheses. Every one of those 4 cases was resolved using instruments that had been built to do something else entirely. A telescope for asteroids, a dish for pulsars, a rover for geology, which raises the obvious question about what happens when the instruments are finally built for this. Part 9. The digs now underway. For most of the last 60 years, this search was a small thing. A handful of people working on borrowed telescope time, using instruments built for other purposes, looking almost exclusively for one specific thing, a live radio signal from a living neighbor in a narrow slice of the spectrum, right now. That is no longer the situation. Everything in this part is real, funded, and either operating tonight or on a published schedule. And the change is not that anyone decided to look harder for civilizations. The change is that the instruments being built for ordinary astronomy have become capable enough that the archaeological question comes along for free. Start with the one that changed last month. The Vera C. Rubin Observatory sits on Cerro Pachon in Chile, and it formally began its main survey, the Legacy Survey of Space and Time, on the night of the 29th of June, 2026. 4 weeks ago. Its camera holds 3,200 megapixels, 3.2 gigapixels, in a single instrument, the largest digital camera ever built for astronomy. Over 10 years, it will image the entire southern sky every few nights, producing something like 15 terabytes of data every night, and around 200 petabytes by the end. But the specification that matters for this video is not the resolution. It is the cadence. Rubin does not look at objects. It looks at everything, over and over, and finds what changed. That is a fundamentally different kind of instrument from a telescope that points at a target. It is a monitoring system for the sky. And that turns the delivery channel from the sixth part of this video into something we are actually watching. Interstellar objects have been found essentially by accident, at a rate of about 1 every 3 years, and always by whichever survey happened to be pointed in the right direction. Rubin is expected to find them regularly. More importantly, it is expected to find them earlier, while they are still inbound, when there is still time to point other instruments at them, or in principle, to send something after one. Remember Project Lyra from the sixth part, the mission concept for chasing down an interstellar object, and the reason it cannot currently be flown. The problem was that we always find them on the way out. Rubin is the instrument that fixes that specific problem, and it started work a month ago. There is one more thing about Rubin worth saying. Its data will be public, and its alert stream, the notification system that flags anything that changed, is designed from the ground up to be consumable by anyone with the interest to consume it. Which means the search is no longer confined to funded institutions. It is available to whoever wants to look, in the same way that the sky over Nokshnij was available to Gennady Borisov. It is worth putting the scale of that data in terms a person can hold. 15 terabytes a night is roughly the entire text and image content of every book ever printed, several times over, every night, for 10 years. No human being will look at most of it. The survey is designed on the assumption that the overwhelming majority of what it records will only ever be examined by software, and that the role of people in the system is to decide what the software should be looking for. Which is a genuinely new situation for this question. For 60 years, the constraint on the search was how much sky anyone could afford to point a telescope at. That constraint is going away. The constraint from here on is what questions we think to ask of an archive that is being filled faster than anyone can read it. An artifact could sit in that dataset for years, correctly recorded, correctly catalogued, and entirely unremarked, simply because nobody had written the query that would surface it. That is not a hypothetical failure mode. It is how a great many discoveries in modern astronomy have actually been made, not at a telescope, but by someone going back through data that had been sitting on a disk for a decade and asking it something new. Radio has scaled up too, and the interesting part is how. Breakthrough Listen was announced at the Royal Society in London on the 20th of July 2015 by Yuri Milner, standing alongside Stephen Hawking. $100 million over 10 years, targeting the 1,000,000 nearest stars and the 100 nearest galaxies. At the time it was, by a wide margin, the largest sum ever committed to this question. It runs on the Green Bank Telescope in West Virginia, on Parkes in Australia, on the 64 dishes of Meerkat in South Africa, and on the automated planet finder at Lick Observatory in California for optical laser searches. And in May 2023, a system called COSMIC came online at the Carl Jansky Very Large Array in New Mexico. What COSMIC does is the design change that matters more than the money. It takes a real-time copy of the data stream from all 27 dishes of the array, while the array is doing its ordinary survey work, and analyses that copy for narrowband signals. It targets about 10 million star systems. Nobody has to allocate telescope time for it. The array is looking at the sky anyway, for entirely different reasons, and COSMIC reads over its shoulder. Meerkat's survey works the same way, examining 1 million stars without requiring a single dedicated observing night. That removes the argument that constrained this field for 50 years. The objection was never that the search was unscientific. The objection was that telescope time is scarce and expensive, and there are 100 proposals competing for every night, and it is very hard to justify spending one of those nights on a search with no track record of success. Riding along on somebody else's observation costs nothing, and so nobody has to say no. The Allen Telescope Array at Hat Creek in Northern California is the one instrument built specifically for this. 42 dishes, 6.1 meters each, owned and operated by the SETI Institute. It has been through a substantial refurbishment since late 2019, with new cryogenically cooled feeds covering a continuous range from 1 to 11 gigahertz and an entirely rebuilt digital backend. The feeds are named for Franklin Antonio, the Qualcomm co-founder who funded the work and who did not live to see it finished. Laser SETI is the optical version, watching for extremely brief flashes rather than continuous radio. It now runs from 4 sites, in California, at Haleakala in Hawaii, in Arizona, and in Puerto Rico, covering something approaching a third of the night sky continuously. There is also a working instrument installed at the Natural History Museum in London. Then there are the instruments that will characterize planets rather than count them, and this is where the next decade gets genuinely interesting. The Nancy Grace Roman Space Telescope is scheduled to launch on the 30th of August this year, about 5 weeks from tonight, on a Falcon Heavy from Kennedy Space Center. It arrived at the Cape in June for final processing, running roughly 8 months ahead of its required readiness date, which is not a sentence one gets to write often about a flagship space telescope. Roman is not a techno-signature mission, and nobody would describe it as one. It is a wide-field infrared observatory, built for dark energy, for a galactic bulge microlensing survey, and for direct imaging of exoplanets with a coronagraph that blocks the light of the host star. But the microlensing survey is worth flagging for our purposes. Microlensing detects objects by the way their gravity briefly magnifies the light of a star passing behind them, and it does not care whether the object emits any light of its own. It is currently the best available method for counting rogue planets, the worlds that have been ejected from their systems and now drift alone between the stars. Estimates put their number in the trillions in this galaxy. That is the population nobody talks about in this context. Every ejected planet is a world that had a history and then lost its star. If any of them ever carried anything, the surface is now at a few tens of degrees above absolute zero, in permanent darkness, geologically dead, and absolutely undisturbed. Whatever is on a rogue planet stays exactly as it was, forever in the dark. They are the largest and least examined preservation medium in the galaxy, and we are about to start counting them properly. The extremely large telescope is under construction at Cerro Armazones in Chile. Its primary mirror is 39 meters across and made of 798 individual segments. Telescope first light is now scheduled for March 2029, with scientific first light in December 2030. That schedule slipped from 2028, and the reasons given were contract delays, site weather, technology development, and manufacturing failures. I include the slip deliberately because that is how these projects actually run, and pretending otherwise does nobody any favors. What the extremely large telescope buys is not magnification, but light. A 39-meter mirror collects roughly 15 times more light than the largest telescopes operating today, and light is the entire constraint on reading the atmosphere of a small planet around another star. The signal is always there. It is simply too faint, and the only cure for too faint is a bigger bucket. With that much collecting area, the spectral features that Lin and his colleagues calculated in the 5th part of this video move from theoretical to routine. Not around white dwarfs, where the geometry does the work for you, but around ordinary stars, around planets that resemble this one. The chemistry of a dead world stops being something you would need a lucky alignment to read. And then there is the Habitable Worlds Observatory, which is the first telescope ever designed from the outset specifically to look for signs of life on other planets. Its goal is to directly image and take spectra of at least 25 Earth-like planets around Sun-like stars within about 30 light-years, hunting for oxygen, ozone, and methane. It is a project of the 2040s, and its funding is genuinely unsettled. It received $150 million in the 2026 appropriation against a request of $3.3 million, and the request for 2027 drops it to $5 million. Those numbers move in both directions, and nothing about the mission is guaranteed. What is settled is the architecture. NASA mandated this July that it be designed for in-space servicing, meaning it is intended from the start to be repaired and upgraded in orbit rather than launched once and abandoned. Let me pause here and imagine something, because everything else in this part is a specification, and the thing that actually matters is what happens on one particular night. Picture the verification. It is late. Somebody is looking at a waterfall plot, which is the standard display in radio astronomy: frequency across, time down, brightness as color. And there is a line on it. Narrow, slightly slanted, running down the plot. Narrow means it is not natural. Slanted means it is drifting, which is what a transmitter on a rotating planet does. And the line is present in the on-source pointings and absent in the off-source ones. 3 checks, all clean. Nobody says anything. What actually happens next is procedural, and the calm of it is the point. The first thing is more nodding. Point at the target, point away, point back, repeat, for hours, because a signal that is genuinely coming from that direction has to keep behaving that way, and local interference eventually will not. Then the interference database, which is a catalog of every known local emitter, every satellite downlink, every airport radar, every piece of equipment on site. Then the check of whether anything in the observatory's own building was running. Then the call to a second telescope, on a different continent, under a different sky, with a different set of local transmitters. Not to announce anything. Simply to ask them to look at a set of coordinates and a frequency and report what they see. And through all of it, nobody says anything publicly, because the last time this happened, the checks took 2 years, and the answer was a mixing product from ordinary human equipment. Everyone in the room remembers that. Everyone in the room has read Sheikh's framework and knows exactly how long the list of things to eliminate is. And then, in this imagined night, the list runs out. The second telescope sees it. The database is clean. The building is quiet. Every category of explanation that has ever accounted for one of these has been checked and eliminated, and there is nothing left on the list. Somebody has to write the next email. And it occurs to whoever it is, sitting there at 4 in the morning, that in the entire history of the species, nobody has ever had to write that particular email before, and that there is no template for it, and that the protocol drafted for exactly this moment is 37 years old and has never once been used. Now, the last category. The missions going to specific places. Europa Clipper launched on the 14th of October, 2024, and is currently mid-cruise. It makes its Earth gravity assist on the 3rd of December this year, about 4 months from now, and arrives at Jupiter in April 2030. Its route covers about 2.9 billion kilometers to reach somewhere that is currently a small fraction of that distance away, which is what gravity assists buy you. You trade distance and time for fuel you do not have. Europa Clipper is worth one more sentence than the schedule because of what it is actually going to do. Europa has a liquid water ocean beneath an ice shell perhaps 15 to 25 kilometers thick, and that ocean has been there for most of the age of the solar system. It contains, by volume, roughly twice as much liquid water as every ocean on this planet combined. The spacecraft will not land, and it will not drill. It will make around 50 close passes, some of them within 25 kilometers of the surface, mapping the ice, measuring the ocean's depth and salinity through its effect on Jupiter's magnetic field, and sampling any material thrown up by plumes. It is a reconnaissance mission for a place that has had 4 billion years of liquid water, chemistry, and energy, and no way for anything living there to ever look up and see a star. Which is its own quiet contribution to this evening's question. If the interesting chemistry in this galaxy is happening under ice, then the search for civilizations and the search for ruins are both looking in the wrong place, and always have been. Dragonfly is a nuclear-powered rotorcraft built by the Johns Hopkins Applied Physics Laboratory. It was confirmed in April 2024 at a life cycle cost of $3.35 billion. It launches in July 2028 and reaches Titan in 2034, where it will become the first powered aircraft to fly between landing sites on another world. And Tianwen-2, from the third part of this video, is already on station at Kamoʻoalewa and will bring a piece of it back in November 2027. So here is where all of that leaves us. For 60 years, this was a handful of people on borrowed time, looking for a live radio signal from a living neighbor. Within the next decade, there will be an observatory cataloging every interstellar visitor that passes through this system. A telescope large enough to read the chemistry of individual rocky planets around other stars. A sample of Earth's closest co-orbital object sitting in a laboratory, and a rover flying through the atmosphere of a moon with liquid on its surface. Not one of those instruments was built to find a ruin. Every single one of them could. Which leaves the question this whole video has been circling. What would actually change on the day somebody found one? Part 10. What it would mean to find a ruin. We come to the last part, and I want to slow down for it. Start with the practical question, because the answer is a good deal more organized than most people would guess. If somebody found something tomorrow, what actually happens? And it turns out there is a procedure, and it has existed for 37 years, and it was written by people who thought carefully about it. In 1989, under the International Academy of Astronautics, a document was adopted with the title Declaration of Principles Concerning Activities Following the Detection of Extraterrestrial Intelligence. It is voluntary. It is non-binding. No government signed it, and no law enforces it. It is a code of professional practice, and it says 4 things. Verify before announcing. Whoever finds something is expected to establish that it is real, using every available means, before telling anyone outside the immediate group. Share the data with the international scientific community so that verification is not confined to the people who have an interest in the result being true. Disclose publicly and promptly once verification is complete. There is no provision for keeping it quiet, and the document is explicit that the discovery belongs to everyone. Notify the Secretary General of the United Nations. And then there is the 5th principle, which is the one that matters most, and the one that has generated the most argument in the decades since. No reply is to be sent on behalf of humanity by any individual, any institution, or any state without prior international consultation. That principle exists because the alternative is that whoever happens to have a transmitter and an opinion gets to answer for the species. It was revised in 2010. A companion document covering the sending of messages was drafted in 1995. Both were presented to the United Nations Committee on the Peaceful Uses of Outer Space in 2000, and a further update has been in preparation since 2022. The argument about that 5th principle is worth a moment, because it is the one live ethical dispute in the whole subject, and it has never been resolved. There are researchers who believe we should be transmitting deliberately, at high power, at nearby stars, on the reasoning that a universe in which everybody listens and nobody speaks is a universe in which nothing is ever heard. There are others who believe that announcing our position to an unknown recipient with unknown intentions is the single most consequential decision our species could take, and that it should certainly not be taken by whoever gets to a transmitter first. Neither side has any evidence, because there is no evidence to be had. What they have is a disagreement about how to behave under total uncertainty, and the protocol's answer is essentially procedural. It does not resolve the argument. It simply says that nobody gets to settle it unilaterally. Which is, I think, the correct answer to an unanswerable question. You cannot decide what to do. You can decide who decides. There is also a scale for describing what has been found, which I find quietly reassuring in the way that a well-designed form is reassuring. Ivan Almar of the Hungarian Academy of Sciences and Jill Tarter of the SETI Institute proposed it in 2000 at the International Astronautical Congress held that year in Rio de Janeiro, and it has been called the Rio scale ever since. It runs from 0 to 10. It combines two things that are usually confused with each other: how significant a detection would be if it were real, and how likely it is that it is real. A single number carries both, so that a claim can be communicated publicly without the significance being mistaken for the confidence. It was substantially rebuilt in 2018 to handle modern cases, including non-radio technosignatures and anomalous objects. There is a scale for this. Somebody sat down and thought it through, and then somebody else improved it 18 years later. Whatever else is true about this field, it has not been careless. Now the consequence, and this is where the argument of the whole video arrives somewhere. If a ruin were found, the immediate scientific question would not be who they were. That question would be unanswerable for a very long time, and possibly forever. The immediate question would be about the Great Filter, and the answer would be uncomfortable in a specific way. Think it through. The remains of a civilization that started, built things, and then stopped is evidence that starting is not the hard part. It would be direct evidence that the sequence from chemistry to technology can be completed, because it was completed there. And if starting is common while continuing is not, then the filter is not behind us. It is ahead, and the effect scales with what is found. A microbial fossil on Mars is a mild concern, because it only tells us that life begins easily, and there are several difficult steps between a microbe and a civilization. But the remains of something that had reached space and then ended would be the most sobering discovery in the history of the subject, because it would have cleared every step we have cleared, and several we have not, and it would still be gone. Set against that, the Oxford result from the 7th part of this video points the other way, and it points quite firmly. When you update on the silence, the improbability loads onto the origin of life, not onto survival. The hard step on that analysis is behind us. The honest position is that we do not know which of those is right, that finding a ruin is one of the few things that would actually settle it, and that the settlement might not be the one anybody wants. That is a fact about the state of our knowledge. It is not a prophecy, and I am not offering it as one. And now the turn, which is where this video has been going since the first sentence. For 3 hours we have been asking what an ancient civilization would leave behind, where it would be, what it would be made of, how long it would last, how we would recognize it if we were looking straight at it. And every part has pointed at the same profile. Something small, something hard, chemically inert so that nothing attacks it. Information carried as physical relief, cut into a surface, requiring no machine, no format, and no power to read. Sitting in vacuum, away from stars, where nothing will disturb it. And, ideally, with a clock built into it, so that whoever finds it can tell how long it has been traveling. We have already made 5 of them. They are not proposals. They are not concepts. They left. 2 plaques of gold anodized aluminium, engraved in 3 weeks by a trophy shop in California, currently further from the sun than anything else our species has sent, except 2 other objects. 2 gold-plated copper records with a pulsar map on the cover locating this star, and a spot of uranium-238 electroplated beside it, so that a finder can date the launch by measuring what has decayed. And a stack of nickel foil holding 30 million pages, believed to be lying in a small debris field on the Moon, on a surface that turns over to a depth of 1 meter every billion years. 1 meter per billion years. We first met that number in the 3rd part of this video, as a search parameter, as the reason the Moon is worth examining for somebody else's artifacts. It comes back now as the survival time of our own. There is one more thing on that list, and it is the one nobody launched anywhere. Lagios 1 is still in orbit, 60 centimeters of brass and glass, doing nothing except being a fixed point for lasers to bounce off. Sealed inside it is the plaque with 3 maps of the continents on it, and the 3rd map is dated to 8.4 million years from now, which is when the satellite is expected to come down. Whoever is standing on this planet on that day, if anyone is, will be able to look at that plaque and work out when it went up by comparing the map to the ground under their feet. No language required. No format to decode. Just the observation that the continents have moved a certain distance and the knowledge of how fast they move. Of the 5, that is the only one addressed to somebody here. And it assumes, without ever saying so, that the recipient may share nothing with us at all. Not a language, not a history, not a species. Only a planet, and the fact that its surface drifts at a rate you can measure. Voyager 1 is currently about 172 astronomical units from the Sun and receding at roughly 17 kilometers per second. On the 18th of November this year, it becomes the first object made by human beings to reach a distance of 1 full light day from Earth. 25.9 billion kilometers. Light itself, which crosses this entire solar system in a matter of hours, now takes a full day to reach it. In about 40,000 years, it passes within roughly 1.6 light-years of a dim red star called Gliese 445 in the constellation Kamoʻoalewa. And after that, it has no scheduled appointments at all. Voyager 2 is out there too, on a different heading, carrying an identical record. It is slower because of the route it took past Neptune, and it is going in almost the opposite direction. In roughly 40,000 years, it makes its own closest approach to a star called Ross 248, and then it also has nothing left on its schedule. So, there are 2 of them. 2 identical objects, launched 16 days apart in the summer of 1977, now separated by a distance that grows every second, both carrying the same 115 images and the same 55 greetings, and the same 90 minutes of music, both with the same uranium spot, quietly running the same clock at exactly the same rate. If either is ever found, the finder will be able to date it. If both are ever found, by anyone, at any point in the next several billion years, the 2 dates will agree. Let me take you out there, at the end, because this is the last thing. Picture it 1,000 years from now. Nothing is transmitting. The plutonium that keeps the instruments warm gave out within a few years of tonight, and the spacecraft has been cold and silent for a millennium. It is a structure, not a machine. The record is still bolted to the side, in its aluminium case, cover facing outward. It does not need the spacecraft. It never did. Now 10,000 years, and the constellations visible from Earth have begun to distort as the nearby stars move against each other. 40,000 years, and it makes its pass by Gliese 445, closer to that star than to our own, and nothing happens, and it carries on. 100,000 years, and the uranium spot on the cover has lost a fraction of a percent of its mass to decay, and the ratio has shifted by an amount that is measurable if anyone measures it. That is all the clock has done. It has barely started. 1,000,000 years. On Earth, whatever is happening is not anything we would recognize. The record is unchanged. Cosmic rays have darkened the surface very slightly. 100 million years, and the plate is roughly as old as the dinosaurs are to us, and the diagrams are still legible, and the pulsar map still resolves to the correct star, even though the pulsars have all slowed measurably, which was the point of writing their periods down. 1 billion years. The sun is noticeably brighter, and the oceans of Earth are in trouble. The uranium has halved a fifth of the way toward its first full half-life. And the object is somewhere in the general volume of the galactic disk, having completed perhaps 4 laps around the center of the Milky Way at roughly 230 million years apiece, going nowhere in particular, expected nowhere, on a trajectory nothing will ever bend. None of which makes it any less legible. That is the thing to hold. It is not lost. Nobody has lost it. It is simply out, and it will keep being out, and the instructions on the cover are as clear in 1 billion years as they were the day they were etched. I should be honest about the readable lifetime one more time, because I have used the figure twice tonight, and it deserves the caveat repeated rather than buried. Around 1 billion years is an estimate. It is not a measurement. Nobody has run the experiment, and the published range extends from about 1 billion to about 5. What we know for certain is the half-life of uranium-238, which is 4.468 billion years, and is not in dispute. The clock is exact. The legibility of the thing the clock is attached to is a projection. So the answer to what an ancient civilization leaves behind turns out not to be hypothetical, and it never required finding anyone. We already know, because we already did it. On a modest budget, in a hurry, without much of a plan, within 7 years of first leaving the atmosphere. We are not early. We are late. That was the first arithmetic of this video, and it was offered as a disadvantage, as the reason we would only ever find remains rather than neighbors. But lateness runs both directions. Being late means somebody came before. It also means somebody comes after. And relative to whoever that is, we are the early ones, and the small hard objects with the clocks on them are already on their way. The ruins we have spent 3 hours looking for turned out to be the ones we are making. They are still going, and they will still be going long after everyone who built them, and everyone who remembers them, is gone. Whatever else is out there tonight, the record is already leaving. Sleep well, and good night.